Imagine you're looking up at the sky on a clear night, and you see all those beautiful stars twinkling up there. Well, one of them is Betelgeuse, a celebrity among stars. If you want to catch a glimpse of it, look up at the Orion constellation. It low-key looks like an archer holding a bow, and you can spot Betelgeuse as the reddish-orange dot on their shoulder. It's one of the brightest stars in the sky, so it's hard to miss. Betelgeuse is not your ordinary star. First of all, it's gigantic, up to 1,000 times the size of our sun. Can you imagine that? It's so enormous that if we could somehow replace our sun with Betelgeuse, it would engulf all the inner planets, including Earth. And here's another fun fact. When we look at Betelgeuse, we're actually looking back in time. Yep, you heard it right. Betelgeuse is about 600 light years away from us, so the light we see today actually left the star 600 years ago. It has quite a history. This star has been shining brightly for millions of years. Long, long ago, even before smartphones and telescopes, ancient Sumerians were the first to spot Betelgeuse in the sky, and it's been a diva this entire time. For example, in 1866, Betelgeuse became one of the brightest stars in the night sky. It was so dazzling that people could see it even during the day. Astronomers all around the world went bananas documenting this extraordinary event. Since then, Betelgeuse has been playing hide-and-seek with us. It all started when Betelgeuse started to dim back in 2019. Since then, it likes to dim and brighten sporadically. But these changes in brightness tell us about something important. As we mentioned, Betelgeuse was always a bit of a troublemaker. It's been living a fast and furious life. Because of that, it has been burning its fuel at an incredibly fast rate. The changes in the star's brightness are clues that Betelgeuse is approaching the end of its life cycle. The drama intensified when the Hubble Space Telescope snapped jaw-dropping images of Betelgeuse, like it was getting ready to blow its top. All this made scientists think that the star is close to retiring in a dramatic way. It's about to go supernova. So picture a star partying hard, powered by the fusion of hydrogen atoms. It's like the star's own energy drink, but just like any party, the fuel starts to run out. That's when things get interesting. As the star guzzles up its hydrogen fuel, it slowly begins to run on empty. It can't sustain itself anymore. So now, it's time for the grand finale. This finale is called supernova. The star collapses in on itself like a deflating balloon. The pressure and temperature inside skyrocket to mind-boggling levels, and this celestial tantrum triggers a colossal bang. So you can see why observing Betelgeuse is like having a front-row seat to the spectacular drama. But here's the big question. When will this happen? Well, the answer is not as simple as setting a timer. You see, stars have their own schedules, and Betelgeuse is no different. It could be tomorrow, or it could be thousands of years from now. Scientists have come up with only a rough estimate. They believe that Betelgeuse will go supernova within the next 100,000 years. Quite a spread, huh? Sure, that sounds like forever to us, tiny humans. But in the vastness of the universe, it's just a blink of an eye. But there's a chance, just a tiny chance, that Betelgeuse could surprise us all and go supernova much sooner. Considering its dips in brightness, we might be in for a show within the next few hundred years. We'll just have to wait and see. Now, if Betelgeuse does go kaboom, what will happen? Well, get ready for a show like no other, folks. When a star collapses under its own weight, it unleashes a cosmic firework of epic proportions. The star releases a crazy amount of energy in the form of light and heat. Betelgeuse's supernova is going to be extra special. It's like the superstar of supernovas. It will shine so brightly that it might even outshine the other stars in the sky. Picture that, Betelgeuse stealing the spotlight. The show could be so bright that you won't need a telescope to catch a glimpse. Nope, you'll be able to see it with a naked eye. It might even be visible during the day, making the sky look like it's hosting the coolest rave ever. After that, the supernova will keep us entertained for weeks, It will be like having a second moon in the sky, shining as bright as the full thing. Imagine that, 2 moons dancing together in the night. After several weeks of lighting up the night sky, Betelgeuse's supernova will slowly fade away, but it would leave behind a souvenir, an ethereal remnant. It's like a fading memory of the star's epic performance. This remnant, too, would slowly fade away over the course of several months. But it's not just about the light show. The boom will send out powerful shockwaves, and we might actually feel them right here on Earth. It's like the universe giving us a gentle tap on the shoulder, saying, "Hey, look at this amazing spectacle. How dangerous will it be for us?" Well, we know that Betelgeuse's supernova would send dust and gas shooting into the atmosphere. It's like a big space sneeze. And this sneeze could cause a decrease in global temperatures. We're talking serious climate impact here. It could even lead to a mini ice age. But these are just assumptions. We don't know for sure if the consequences will really be that serious. But, of course, we want to be prepared for this event just in case. That's why scientists are studying Betelgeuse closely. But, in addition to serious scientific research, astronomers also have a blast of celestial comedy. Jokes are flying left and right. Someone has even created a Betelgeuse status account, which you can check yourself. So, as you can see, the star is keeping us on our toes. Astronomers keep observing it, and they need our help too. They want us to keep an eye on Betelgeuse and report any changes we see. How do you do that? First off, channel your inner astronomer and observe Betelgeuse. Take a peek at the star and note down what you see. Is it twinkling, shining, or feeling a bit dim? Jot it all down. Then be a superstar yourself and report your observations to the astronomers. Your observations will help them track Betelgeuse's journey towards its big supernova moment. You can also join in on some citizen science projects. They're super fun and easy, trust me. One cool project you can jump into is the Betelgeuse Brightness Monitor. By participating, you help scientists keep tabs on how bright Betelgeuse is shining. Your contribution can make a real difference. So join the monitoring team. You'll be part of something amazing, and who knows, your observations might even help predict when Betelgeuse will show off its supernova magic. By doing that, we can assist them in monitoring this superstar and learn more about the fascinating world of stars. But that's how we can help scientists to predict this event. Now, how can you personally prepare for it? First things first, you'll need the right gear to catch all the supernova action. A trusty telescope is like your front row ticket to the starry show. It'll bring you up close and personal with Betelgeuse's performance. And remember, you'll need special eyewear to shield your eyes from the intense burst of light. Safety first. And of course, prepare in case it decides to mess with our climate. Stock up on essentials, like warm clothes and supplies, just in case we experience a mini ice age. But let's just hope it won't happen. So keep your eyes on the night sky, my friends. Betelgeuse may not be ready to blow up just yet, but when it does, it will be a sight to behold. Until then, let's enjoy the twinkling stars. And remember, there's always something extraordinary happening in the vastness of space.
Most of those twinkling dots scattered across the night sky seem unreachable. But one of them is Betelgeuse, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Betelgeuse. It's one of the brightest stars we can see from Earth. And it's just 640 light years away. No big deal. Betelgeuse has a blue-white O-type star, which is one of the hottest types to exist. Betelgeuse was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star, and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Betelgeuse. it burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Betelgeuse replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Betelgeuse spinning way faster than it should for a star of its size. Huge stars like Betelgeuse are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Betelgeuse's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Betelgeuse shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Betelgeuse's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Betelgeuse isn't as smooth as our Sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the Sun, but Earth's entire orbit around the Sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Betelgeuse could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Betelgeuse dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Betelgeuse clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Betelgeuse cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Betelgeuse's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Betelgeuse might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Betelgeuse run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Betelgeuse supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Betelgeuse will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Betelgeuse explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Betelgeuse might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Betelgeuse is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Betelgeuse might have less than 300 years of fuel left in its core. They say that Betelgeuse is known to expand and contract regularly, and its pulsation pattern hints that Betelgeuse is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VYCMA in our galaxy is thought to be closer to going supernova than Betelgeuse, and it's been dimming steadily over the past century, unlike the relatively stable Betelgeuse. If Betelgeuse was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Betelgeuse as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Betelgeuse won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm.
Now, it's been a long time since there was a supernova in the Milky Way. Over 400 years to be precise. So hey, we're long overdue. So here are the most likely stars to go boom, if they haven't already. At the top of the list must be the southern hemisphere star Eta Carinae. Greek letters before the name of the constellation indicate the rank of the star's brightness in that constellation. Sir Edmund Halley, in 1677, recorded Eta Carinae as the 7th brightest star in the constellation Carina, Eta being the 7th letter in the Greek alphabet. It might not have looked very bright to Sir Edmund and his contemporaries in the 17th century, but modern studies of Eta Carinae estimate it's 5 million times more luminous than our Sun. Luminous is a technical word astronomers use. It doesn't just mean brightness. Luminosity refers to the total energy released at all frequencies. Eta Carinae releases 5 million times more energy than the Sun. Truly one of the whoppers of the Milky Way, Eta Carinae is 100 times more massive and 240 times larger than our yellow-white dwarf sun, Sol. Obviously, since it appears dim, Eta Carinae is pretty far away, about 7,500 light-years away. Yet even at this distance, if this star goes hypernova, it can still impact Earth's ozone layer, disrupt satellite communications, and harm astronauts. 159 years after Halley's observation, Eta Carinae experienced a nova-like explosion. It increased from a relatively dim star to become the second brightest star visible from Earth, but only for a period of 27 years. From 1836 until 1863, Eta Carinae was the second brightest visible star after Sirius, the dog star, and Sirius is only about 8 light-years away. Since 1863, aside from a couple of flare-ups, Eta Carinae has dimmed back down to its original brightness at magnitude 4.5. Now, astronomers owe us a small apology, which we don't expect to get anytime soon, for star magnitude nomenclature. The brighter a star is, or planet, or moon, the lower its magnitude. Thus, stars brighter than first magnitude are either zero magnitude or negative magnitude. The full moon, for example, is magnitude negative 13. A magnitude positive 4.5 star, like Eta Carinae, is quite dim as seen from Earth, but it's clearly visible in a night sky without light pollution or clouds if you live anywhere south of the latitude of Cairo, Egypt. 30 degrees north latitude is the farthest north you can see this star. Now, listen up. Eta Carinae is currently up to something. It's been brightening again and is now brighter than at any time since 1864. It's a complex situation. Eta Carinae is really two stars, Eta Carinae A and Eta Carinae, what's your guess? Oh, B. There's a third star nearby that's also interacting with the double star's dynamics. Now, without looking, I'm guessing it's named Eta Carinae C. Good guess. Blown out into two incredibly massive globes of gas that are expanding at 20 million miles per hour, Eta Carinae is, without a doubt, one of the strangest looking stars you'll ever see. Remember, it's located at a great distance of 7,500 light-years away from us. And if anything had happened to Eta Carinae in the last 7,500 years, like going hypernova, we wouldn't be able to see it, because none of Eta Carinae's electromagnetic radiation would have gotten here yet. Astronomers are keeping a close watch on Eta Carinae because it can go hypernova at any time. Or maybe it already did 5,000 years ago, in which case we'd only have to wait another 2,500 years to see it. Yeah, like I'll put it in my planner. Now, from a list of over 30 likely candidate stars that might go supernova, Rho Cassiopeiae is many astronomers' choice. Another Greek letter, Rho, is the 17th letter in the Greek alphabet. It means that Rho Cassiopeiae is the star with the 17th brightest apparent magnitude in the constellation Cassiopeia. Yet Rho Cass, a nickname, is only one of 7 known yellow hypergiant stars in the Milky Way. It's another whopper. To be seen at magnitude 4.5 from a distance of about 10,000 light-years away, Rho Cass must be a very large star, a hypergiant. Placed where the Sun is, Rho Cass would encompass the orbit of Mars. But it's still yellow. It's not a red giant star. Red indicates a cooler surface temperature. Rho Cass, as huge as it is still as hot on its surface as our Sun, or even a little hotter. That can only mean two things. Deep inside its core, Rho Cass is fusing atoms much heavier than hydrogen or helium. Plus, Rho Cass is producing much more energy than a red giant star. In the year 2000, Rho Cass erupted massively. It brightened by 2 orders of magnitude as it ejected 10,000 times the mass of Earth into space at 4 times the speed of sound. Astronomers detected the signature of titanium oxide in this eruption. This means that Rho Cass is much closer to going supernova, or in this particular case, hypernova, than astronomers used to assume. Iron is just a few steps above titanium in the periodic table, and when iron forms, fusion stops and a star collapses. Rho Cass is really close, or more correctly, was really close. Because the eruption we saw in the year 2000 really happened 10,000 years before, many astronomers think Rho Cass has already gone hypernova, formed a black hole, and doesn't even exist anymore. Meanwhile, Betelgeuse caught everyone's attention not so long ago. The star, not the movie. It dimmed dramatically, appearing only 37% as bright as it usually is. Is it getting ready to go supernova? Betelgeuse is by far the brightest star in the whole sky, in infrared light. This is an important fact because it relates to Betelgeuse's status as a supernova candidate, as we shall soon see. Betelgeuse is also named Alpha Orionis, another Greek letter designation. So we should conclude that Betelgeuse is the brightest star in Orion, right? Wrong. It's the second brightest star in its constellation. Rigel, or Beta Orionis, is the brightest one in that region. Figure that one out. It may be because Betelgeuse is classified as a semi-regular variable star, which sounds kind of redundant to me. Its approximately 400-day cycle of pulsation changes its brightness by about 1 full magnitude, going from much brighter than a first magnitude star to closer to a second magnitude star. But never was Betelgeuse observed to dim so rapidly or so drastically as it did recently. So what's going on with it? Well, from late 2019 to mid-2020, Betelgeuse went through a period of substantial dimming during a mass ejection event. The world astronomy community jumped on the situation, and in the course of their investigations, they came up with some surprising new factual data on Betelgeuse. First, Betelgeuse is not as far away as we once thought. The new, more accurate distance for Betelgeuse is 548 light-years. That's 25% closer than previously measured. The second new fact, Betelgeuse's diameter has been reduced by the same percentage. The star is now known to be 25% smaller than previously believed. The cause of Betelgeuse's dramatic dimming was also determined. The giant star ejected a cloud of gas that contained magnesium. The cloud blocked a large portion of the light coming from Betelgeuse and made it appear visually much dimmer than it really was. Magnesium is not halfway to iron on the periodic table, which means Betelgeuse is not as far along on the path to a supernova as was suspected previously. When iron starts forming in the star, it means that this star is close to shutting down its fusion reactions. The next step is implosion. We aren't quite there yet with Betelgeuse. This star emits most of its energy as infrared light, and it also indicates that its core is most probably still burning helium, and not something that would greatly increase the amount of heat, like carbon for instance. Betelgeuse will still go supernova, but not for another 100,000 years. So you can cross it off your supernova list for the time being. And as for how to correctly pronounce Betelgeuse, you can say it any way you like. There are as many different pronunciations out there as there are people who think they know how to pronounce it correctly. Now, supernova 1987A caught astronomers off guard when it lit up the large Magellanic Cloud 100,000 plus light-years away from the Milky Way. That's when attention was turned to a similar star much closer to Earth, Rigel, in the constellation of Orion. Could Rigel surprise us and suddenly go supernova? There's something called the supernova problem that you should, probably know about because it may relate to Rigel going supernova or not. It seems that stars over 17 solar masses don't always go supernova. Recently, a red giant star simply vanished. Once again, it didn't go supernova, it disappeared. This had often been happening in computer simulations of supernovae, and now it finally occurred in real life. Rigel's mass is 21 solar masses. In other words, it's 21 times more massive than our Sun. So, will Rigel go supernova or simply vanish into a black hole that it'll create in its core? Astronomers and physicists continue their work of learning more about the dynamics of massive stars, scouring the sky for the next supernova in the Milky Way. Meanwhile, we can rest confident that we on Earth are in no danger from the harmful effects of nearby supernova explosions. We live in a nice, quiet, peaceful, stellar neighborhood, except for those Martians next door.
You may be witness of a nova explosion visible to the naked eye any day now. At any point between these days and September, a white dwarf will go thermonuclear. Look at the northern sky over there and follow the arm of the Big Dipper as it arcs toward that star. The name of this star is Arcturus. Somewhere in the middle of that arc, there's the Northern Star constellation. Looks like a smiley face, right? So, sometime in the next 4 months, you might look to the left-hand side of the Northern Star and spot something looking like a new star. It'll shine for 5 days or so. This star system is known as T Coronae Borealis, the blaze star. Most of the time, it's too dim for people to see with the naked eye, but once every 80 years or so, a powerful thermonuclear reaction makes it more than 10,000 times brighter. The last time it happened was in 1946, and now it's our turn to see it. T Coronae Borealis is a binary system, which means it's actually 2 stars. One of these stars is a white dwarf, an old star that has already gone through its fusion-powered life cycle from a main sequence star to just a giant star. The outer parts of such giant stars are eventually pushed into outer space, and what's left behind is a leftover core. That's what we call a white dwarf. At its white dwarf stage, a star is usually super peaceful. You can think of this period as its stellar retirement. Nuclear fusion reactions no longer take place, which makes white dwarfs incredibly dim. At the same time though, they're still quite hot and super dense. Their mass can be compared to that of our Sun, squeezed into the volume of Earth. Strangely enough, the retirement of that white dwarf in T Coronae Borealis is far from peaceful. This is because it has a neighbor which is really prone to littering. You can see that this other star is in its red giant phase. It's actually puffed up, and its outer parts are getting pushed into space. No wonder the material coming off the red giant is falling onto the poor white dwarf. The thing is, it doesn't take much more extra material for the white dwarfs to explode. The matter coming from the red giant will keep accumulating on the surface of the other star until it forms a layer with the depth of a swimming pool. Most material from the red giant is hydrogen, and since the white dwarf is incredibly hot, eventually there will be a spark triggering a runaway nuclear reaction and causing the explosion. The explosion is classified as a nova, which means that it won't eliminate the white dwarf or the red giant like a supernova would. Just around 5% of the hydrogen layer is going to fuse into heavier elements, like helium. As for the rest, it'll get ejected into space. After that, the process will start all over again. You see, such an explosion isn't enough to disrupt the red giant, the supplier of all that oxygen. So, it will just keep doing its own thing. This is also the reason why we can't predict when this cosmic firework will happen. Predictions in astronomy can be super precise. For example, we can calculate that an eclipse will pass over a specific city at a particular time, but other predictions can be really approximate, like, well, this star is going to explode sometime between May and September, or even a bit outside that window. Astronomers have been able to estimate this period only because they know what the events leading to the previous T Coronae Borealis explosion looked like in 1946, and now these signs are repeating. At the moment, many high-precision observatories are zeroed in on T Coronae Borealis to observe the rare cosmic event.
Chubilsky's star was discovered in the 1960s. Since then, astronomers have been intrigued by its unique chemical makeup. The star is suspected to contain ultra-rare elements, verging on the almost impossible. Using special equipment on the European Southern Observatory's telescope in Chile, researchers took readings of the star's magnetic field. They discovered that the star's rotation period, which is the time it takes to finish one revolution on its axis, stretches out over almost 200 years, which is super slow. Of course, there are even more bizarre objects called apstars. They're a chemically interesting category of stars that rotate extremely slowly, with one rotation taking up to 1,000 years. What makes these stars even more peculiar is a wide range of chemical elements astronomers detect when analyzing their stellar spectrums. But if we look at Chubilsky's star, we'll see that it's both similar to and different from other apstars. It contains unusually low amounts of iron and nickel. Our Sun has 10 times more and incredibly high amounts of rare, heavy elements. Those might include strontium, cesium, and neodymium, as well as at least 2 undiscovered elements. They wouldn't occur through any natural processes we currently understand. There's a hypothesis that the presence of such heavy elements could be caused by a star's unseen companion, like a neutron star. Some people go as far as to say that such an incredible chemical makeup could be a sign of an alien techno-signature. Any specialist will tell you that it's the strangest stellar spectrum they've ever observed. Some even claim that there are so many chemical indicator lines you can't immediately understand what you're looking at while observing the star's spectrum. Chubilsky's star also contains high levels of radioactive elements that take a few thousand years to decay. And here's where another mystery lies. They should have long vanished from the star. After all, it's almost 1.5 billion years old. Scientists haven't managed to figure out the reason for the presence of these elements yet. Maybe it's the combination of the star's rare qualities. It spins very slowly, it's hot, and it has a strong magnetic field. This could raise to the surface atoms that would normally be mixed inside the star. There's another theory that explains the presence of these radioactive elements. They could be there as if they were themselves decayed forms of ultra-heavy elements that we haven't discovered yet. So far, no one has been able to prove this theory. Even the discovery of Chubilsky's star's super slow rotation doesn't bring us closer to the answer. It's obvious that there's a lot to learn about the bizarre star, and who knows which secret it still has up its sleeve. Another not less mysterious star is called Tabby's star. It's a sun-like orb around 1,500 light-years away from Earth, sitting in Cygnus the Swan. Unlike our Sun, This star dims randomly by 5 to 22%, and it lasts for days at a time. The reason could be a giant planet passing in front of the star, but then the eclipses would be more regular and not so random. And if it was a Jupiter-sized planet, it would also need to block around 1% of the star's light, which would make it unique and unlike anything we know. After American astronomer Tabitha Boyajian discovered the star's massive and irregular fluctuations in 2015, further observations followed. They show that the overall magnitude of the star has been gradually dimming over the years. Some theories trying to explain this phenomenon are quite believable. For example, some scientists think that these brightness changes are intrinsic to the star. They could be caused by its magnetism or changes in heat flow in its interior. Other ideas are more daring, including some kinds of activity of an extraterrestrial civilization. One of the most plausible theories, though, is that the dimming is caused by the chunks of an orphaned exomoon. It could have been pulled away from its parent planet by gravitational interactions with Tabby's star. As the moon approached the star, it exploded, sending dust clouds into stellar orbit. These countless chunks of rock and dust are now moving between Tabby's star and Earth in a giant, clumpy cloud. It could indeed explain why we observe such irregular brightness variations. Usually, when astronomers spot a spiral arm structure, it turns out to be a galaxy. But not in this case. SAO 206462, located 460 light-years away from our home planet, is a young star. It's surrounded by a circular disk of gas and clearly defined spiral arms. The bizarre star was spotted during an exoplanet search with the help of the Subaru telescope located in Hawaii. Instead of finding fully fledged planets around a young star, astronomers discovered planets that were still in formation. These baby planets are growing out of the disk of gas and dust surrounding the star. The disk extends out to around 80 astronomical units, which is twice the orbit of Pluto. At least 2 of these planets have stretched the disk into its extremely unusual spiral shape. A different planet is responsible for each arm. In our home galaxy, there's a giant star that is a real stellar wind machine. At the moment, this monster is just waiting to burst and send a wave of radiation and hot gas towards Earth. All because it's a Wolf-Rayet, a star which is at that precarious point before it goes supernova. Its core doesn't have any more helium left to burn. Instead, the star is forced to churn through much heavier elements, for example, oxygen. Unfortunately, it disrupts the careful balance between gravity and fusion, leading to the star shedding its layers. When the oxygen eventually runs out, the star will go supernova, but this time the show will be different. The thing is, WR104 is 1/2 of a binary pair, which means that 2 stars are feeding into each other, spinning up their stellar winds. It will continue until they start going incredibly fast. Is the potential explosion going to harm Earth? On the one hand, we're far away enough for even a directed supernova to not hurt our planet. At the same time, there's a threat of an extremely dangerous gamma-ray burst. Luckily for us, it takes a very specific and unlikely train of events for a Wolf-Rayet to produce a gamma-ray burst. Plus, even if it does, the star might be pointed far away enough for the danger to miss us. Anyway, astronomers are still watching the star, just in case. A star sitting in the constellation of Centaurus keeps a secret not many know about. At first glance, it looks like a dim white dwarf, but when astronomers analyzed it, it turns out to be incredibly dense. Take the mass of the Sun and cram it into something that is only 1/3 the diameter of Earth. This space wonder is also rather cool. Its core temperature is a mere 11,900 degrees Fahrenheit. For comparison, the Sun's core temperature is around 27 million degrees Fahrenheit. At such low temperatures, stars begin to vibrate, and then scientists can use these vibrations to sneak a peek inside a star. And in the case with the star in question, which was later named Lucy, they discovered that its carbon core had crystallized. In other words, it formed a giant diamond 10 billion trillion carats in size. Since the discovery of Lucy, a few other crystallized stars have been spotted. Some of them have diamond hearts the size of our planet. The last bizarre star for today is called Vega, and it's squashed. The star's bulging waistline is caused by an extremely high spin rate. Vega rotates once every 12.5 hours. This pushes the material around its equator outward. It also leads to the phenomenon known as gravity darkening, when stellar material further from the center of the star experiences less gravity, which makes it cooler and darker. So when Vega faces Earth pole end on, it looks perfectly round. But the dark halo around its middle is a telltale sign of Vega's oblate shape.
Now see here, astronomers have recently discovered a neutron star, also known as a dead star, spinning at an extraordinary speed of 716 times per second. It makes it one of the fastest spinning stars we've ever found in the universe. And it's not just about its speed. The surface of this neutron star is erupting with super powerful explosions almost non-stop. But before we dig deeper into the mystery of this neutron star, let's figure out what these stars really are. They form from the remnants of massive stars that are at least 8 times the mass of the Sun. When such stars exhaust their nuclear fuel, they can no longer counteract the force of gravity pulling their matter inward. This leads to the collapse of their cores, triggering a massive supernova explosion that blows away the outer layers of the star. What's left behind is an ultra-dense core. That's a neutron star. These stellar remnants are incredibly small, typically just 12 miles wide. At the same time, they pack in more mass than the Sun. The density of neutron stars is also overwhelming. Imagine taking the mass of 2 suns and squeezing it into a sphere about the size of a city. A single teaspoon of neutron star material would weigh around 10 million tons. That's the same as the combined weight of 85,000 blue whales. Such an extraordinary density is what gives neutron stars their immensely powerful gravitational fields. When matter falls onto a neutron star, it accelerates to speeds of millions of miles per hour before slamming into the surface. The energy release from such impacts is truly astonishing. Now, despite its name, inside a neutron star, there are not only neutrons. A few protons survive down there too. Now, normally, protons repel each other since they have the same positive charge. But in a neutron star, that crushing gravity forces them so close together that the strong nuclear force takes over. It pulls them toward the neutrons like they're all part of the same team. Inside the star, things get stranger the deeper you go. Near the surface, neutrons clump into blobs, kind of like a neutron gnocchi. A bit further down, these blobs link together into long chains, forming what scientists call the spaghetti layer. I'm getting hungry. At even greater pressures, the spaghetti chains fuse side by side, creating flat sheets. Think neutron lasagna. Keep going any deeper, and the lasagna eventually breaks down into a uniform mass. But even then, the structure isn't smooth. There are gaps, long tube-shaped voids that look a lot like penny pasta. So inside a neutron star, you've got layers of gnocchi, spaghetti, lasagna, and penny pasta. And each of them represents the mind-bending results of physics under insane pressure. Okay, I'm definitely having Italian for lunch today. Now, the recently discovered neutron star is part of a binary system located in a dense star cluster. This cluster is situated near the center of the Milky Way galaxy, approximately 26,000 light-years from Earth, in the direction of the Sagittarius constellation. The record-breaking spin of the star is extraordinary. If we take a period of not a second, but a minute, it'll be over 42,000 revolutions per minute. At the same time, the newbie ties with another neutron star, which spins at the exact same speed. Such extreme rotation rates are rare and make these stars cosmic outliers in terms of behavior and properties. Oh wait, we can't but mention our neutron star's binary partner. It's a white dwarf, a dense remnant of a star similar in size to our Sun. This white dwarf is pretty fast too. It orbits the neutron star once every 11 minutes. This makes the couple a binary system, with the shortest orbital period ever observed. Imagine a stellar object zipping around its partner faster than the time it takes to prepare a cup of coffee. Yep, that's the kind of speed we're talking about here. This tight, rapid orbit shows how powerful gravitational forces are inside the system. So you might be wondering what makes neutron stars spin so rapidly. It's something called the conservation of angular momentum. Let me explain. When a massive star collapses into a neutron star, it shrinks dramatically. Such a rapid compression gives an instant boost to its spin. It's like an ice skater spinning faster when they pull their arms inward. And the smaller the star gets, the faster it spins, which results in extreme rotation rates. In binary systems like this one, neutron stars can achieve even faster spin rates. Their trick is to steal matter from their companion stars. This process is called theft. No, accretion. The stolen matter carries that very angular momentum, which adds to the neutron star's rotation speed. The accreted material can also build up on the neutron star's surface eventually. It triggers powerful thermonuclear explosions. They release immense amounts of energy, temporarily making the neutron star shine up to 100,000 times brighter than our Sun. It allows astronomers to study the intricate details of these extreme environments. NASA's X-ray instrument on board the International Space Station, officially called the Neutron Star Interior Composition Explorer and thankfully nicknamed NICER, observed 15 thermonuclear explosions on the surface of our neutron star between 2017 and 2021. One of those bursts displayed a unique pattern called thermonuclear burst oscillations. Those are highly asymmetric patches of brightness on the burning surface layers of accreting neutron stars. This pattern matched the spin rate of the neutron star and thus confirmed its extreme rotational speed. But wait, the best part is coming. While neutron stars are already extreme, there's another class of them that takes things to a whole new level – magnetars. Now, magnetars are neutron stars with unimaginably strong magnetic fields, up to 1,000 trillion times stronger than Earth's magnetic field. These fields set them apart from other neutron stars. They can distort atoms in nearby objects, making life impossible anywhere near them. As for the energy density of a magnetar's magnetic field, it's so high that it's 10,000 times greater than the mass density of lead. Magnetars also produce bursts of X-rays and gamma rays that are so powerful they can temporarily outshine entire galaxies. These bursts are often triggered by star quakes, violent shifts in the magnetar's crust caused by their own magnetic fields. For example, a gamma-ray burst from a magnetar in 2004 was so strong that it disrupted Earth's ionosphere. It hit Earth, and it was so intense that several satellites picked it up. The SWIFT satellite, built specifically to detect gamma-ray bursts from across the universe, didn't just detect the blast. It got hit with so much energy that its sensors got completely overloaded. And SWIFT wasn't even facing the burst. The energy was so strong it passed through the spacecraft and still overwhelmed its cameras. If a magnetar was located as close to Earth as the Moon, its magnetic field would erase all credit card data on the planet by wiping the magnetic stripes clean. Whoa, that's the level of power we're dealing with here. Magnetars are extremely active, but for a relatively short time. Their intense magnetic fields decay after about 10,000 years. After that, they stop emitting strong X-rays and gamma rays. Astronomers think that there are at least 30 million inactive magnetars in the Milky Way galaxy alone. These silent cosmic relics are scattered all over the galaxy. Neutron stars and magnetars serve as laboratories for extreme physics. They allow astronomers to have insights into the behavior of certain matter under conditions you can never replicate on Earth. The incredible density of these objects helps scientists figure out what happens when protons and electrons get compressed together to form neutrons. This creates states of matter that don't exist anywhere else in the universe. These violent explosions on neutron stars and magnetars also play a critical role in the formation of heavy elements like gold and platinum. These elements get scattered all over the universe during these energetic events, eventually becoming parts of planets and stars and you and me. Oh, by the way, NASA's NICER instrument has played the key role in uncovering the mysteries of neutron stars. Its ability to detect X-rays with high precision allowed astronomers to study the rapid spin of the neutron star we've been talking about and the thermonuclear bursts that occur on its surface. So, what could be nicer than that? Now, imagine something so powerful that it could rip the atoms of your body apart in a fraction of a second. Ow! This something is soundlessly dashing through space, not extinct, not alive, stuck in between. If this terrifying monster were moving towards Earth, we'd be doomed. So, is it? Astronomers have found a fast and powerful space object zooming through our home Milky Way galaxy at over 110,000 miles per hour, as faster than any rocket we've ever made. This bizarre space object got its name of a zombie star, all because it's the leftover part of a star that passed away a long time ago but is still moving. This zombie star is a kind of an object called a magnetar, a super small, super heavy ball about the size of a city but heavier than the Sun. That makes it one of the densest objects in space. Only black holes are denser. Hey, let's not forget about me, huh? Magnetars also have an incredibly strong magnetic field. The one our zombie guy has is 100 trillion times stronger than Earth's. That's so strong that if the magnetar came close to Earth, it could wipe out every credit card on the planet just from its magnetism, and we couldn't shop anymore. Plus, if a person got too close to a magnetar, like 600 miles or so, it could pull their very atoms apart, and they couldn't shop anymore. Luckily, this magnetar is very far away and not coming near us. When it was first discovered, it was about 15,000 light-years away from Earth. That's a huge distance, so you don't get to worry about your atoms being disconnected yet. Astronomers first spotted the zombie magnetar in 2008. And since only about 30 magnetars are known in our galaxy, it was a lucky and rare find. Scientists use space telescopes like Hubble and Gaia to watch it over time. That's how they discovered it was moving much faster than they thought. Now, astronomers are trying to figure out how this zombie star got such a big kick. At first, they thought that, like most magnetars, this one was born when a giant star exploded in a supernova and the leftover core became a super-dense neutron star. According to their theory, it could have happened near something called supernova remnant HB9. That would make sense since most magnetars are created this way. But when they tracked its movement, they found that the zombie star was moving too fast and going in the wrong direction to have come from HB9. They traced its path thousands of years into the past and still couldn't find any exploding star or star cluster it could have come from. This means scientists now have one more mystery on their hands. Where did this zombie star come from, and how was it made? One explanation is that it came from a white dwarf, which is the leftover core of a smaller star like our Sun after it runs out of fuel. Now normally, when white dwarfs explode, they're destroyed completely. But in rare situations, instead of blowing apart, a white dwarf might collapse into itself and turn into a neutron star. This neutron star could then become a magnetar. This unusual way of forming a magnetar also gives clues about another mystery: fast radio bursts, or FRBs. These are very quick and powerful flashes of radio energy from deep space. Some FRBs come from galaxies that are so old there shouldn't be any exploding stars left. But if magnetars can be born from collapsing white dwarfs, that might explain how those FRBs are still happening. In any case, learning how magnetars form could help us explain many strange and powerful events we see across the universe. But so far, the investigation is still on, and no answers have been found yet. Zombie stars wandering across the universe isn't the only mystery we haven't solved yet. At one point, you might come across one of them while traveling through the cosmos. It looks like nothing. At a distance of 700 million light-years away from Earth, there's a hole, a blank void that has very few galaxies. This is a roughly spherical region about 330 million light-years across. Our home Milky Way galaxy could fit there thousands of times over. It's the mysterious Boötes Void in the constellation of Boötes. Yeah, makes sense. You see, galaxies look like a giant web. Most of them are parts of long structures called filaments. Those wind through the cosmos, and when they meet, they form regions with a high concentration of galaxies. These regions are what we know as galaxy clusters. But between these clusters and threads, there are huge, empty voids that hardly contain any galaxies. Such voids make up almost 80% of the observable universe, and most of them are huge, from 30 to 300 million light-years wide. The Boötes Void is one of the most massive ones. It has even earned the title of supervoid. Astronomers think it might be the result of a few smaller voids merging. But what could have caused such giant empty areas to appear in the first place? The reason might lie in the origin of the universe. In its early days, I wasn't around then, all the matter in the universe was packed together quite tightly. Astronomers even thought it was something like a uniform soup. But soon, random quantum fluctuations started disturbing this matter. Some areas became denser, and their gravitational pull became stronger. They began stealing matter from less dense regions. This made such areas even denser, and they kept attracting more and more matter. At the same time, smaller clumps of matter started drifting further away from the center, forming galaxies. If you visited a star cluster called Palomar 5, you'd forget all about voids and supervoids and even zombie stars. Instead, you'd need to concentrate on surviving, since the region is hiding a swarm of over 100 black holes right in the middle. And those black holes aren't just sitting there, they're at work, shaping the cluster nonstop. Palomar 5 is a group of stars located about 80,000 light-years away from us. Normally, clusters like this are dense and tightly packed, with stars all bunched up together. But Palomar 5 is different. It's spread out and has a huge tail of stars, stretching across 30,000 light-years. This beautiful tail is called a tidal stream. It's like the stars are spilling out of the cluster, creating a long river of light. Tidal streams like this are rare and hard to study. Globular clusters like this one are super old. Some are almost as old as the universe itself. But Palomar 5 also stands out because it's the only cluster we know about that still has a tidal stream attached to it. And the black holes inside the cluster might be to blame. They're pulling on the stars in the cluster, messing with their orbits, and slingshotting them right out of the cluster. Or would that be slingshooting? I don't know. Anyway, these stars are what make up the tidal stream. Over time, more and more stars get flung out. Palomar 5 has way more black holes than expected. About 20% of the cluster's mass is made up of black holes, over 100 of them, each about 20 times the mass of our Sun. Of course, Palomar 5 isn't going to last forever. In about 1 billion years, the cluster will completely fall apart. By then, all the stars will have been gone, leaving behind just the black holes. And these black holes will orbit the Milky Way, like a ghostly remnant of a cluster that used to be there. Even though this cluster is creepy enough, there's something even more eerie you can see in space. Thick clouds of gas and dust called nebulae. One of the most unusual ones is probably NGC 2392, located 5,000 light-years away from Earth in the constellation of Gemini. It was discovered more than 200 years ago and became popular because of its unusual appearance. It's basically a disk of material with a ring of comet-shaped objects. The tails of these objects stream away from the star at the center of the nebula. The bizarre orange streaks in the outer part of the cloud stretch light-years away in all directions. The middle resembles a ball of twine, but in reality, it's a bubble of material blown into space by the wind of high-speed material produced by the central star. Wow. Now, I don't want to freak you out, but something bizarre has erupted in the depths of space. It was an explosion brighter than billions of suns. But the real mystery is that it doesn't match anything astronomers have ever seen. Usually, cosmic events like this follow familiar patterns, but not this one. It's a cosmic anomaly. This strange cosmic explosion has left astronomers totally baffled. It could be a super rare event where everything lines up just right, or it could be something completely new, never seen before. This event was first detected by an X-ray space telescope called the Einstein Probe on April 8, 2024. It first appeared to be a regular gamma-ray burst. Those typically give off incredibly bright X-rays. But could the answer really be so simple? Something didn't add up. Now, gamma-ray bursts are the most powerful explosions in the universe, and they can happen in unusual ways. Long-duration gamma-ray bursts are caused by the demise of massive stars that spin incredibly quickly. When these stars run out of fuel, their cores collapse under gravity, forming an extremely dense object like a black hole. At the same time, the outer layers of the star are blown away in a massive explosion called a supernova. Gamma-ray bursts are followed by jets. Those are twin beams of material shooting out from opposite sides of the collapsing object. They're super fast, moving at nearly the speed of light. These jets appear brighter if they're pointed directly at us. It's like how a flashlight beam is brightest when it's aimed straight at you rather than at an angle. Now back to our unusual cosmic explosion. Remember me telling you something wasn't adding up? Hey, it was just 45 seconds ago. Well, the problem was that when multiple telescopes observed this event in different wavelengths – ultraviolet, optical, near-infrared, radio, X-rays, gamma rays, you name it – it didn't match any known type of event. The most likely explanation, according to current research, is that this explosion is the result of a white dwarf star being torn apart by a medium-sized black hole. And still, it's not so simple. Now, black holes are areas in space where gravity is so strong that nothing, not even light, can escape. That's why they're called black holes. It's believed that stars with at least 3 times the mass of our Sun can collapse under their own gravity once they run out of their stellar fuel. When a star has so much mass packed into such a small space, its gravity becomes so powerful that it forces everything, including atoms, to squish together. This intense density leads to the formation of a black hole. So, when a white dwarf star is torn apart by a medium-sized black hole, it results in a high-speed jet of material that can be aimed directly at Earth. So, could this space disaster be the reason behind our mysterious event? Unfortunately, even though it ticks some boxes for several types of phenomena, including the one involving a white dwarf, it still doesn't fit all the criteria for any of them. The event's short duration and high luminosity are hard to explain using any scenarios we can produce. So, does it mean we have come across something completely new? The universe is full of energetic flashes caused by outbursts from stars and black holes, supernova explosions, stars being eaten by black holes, and other cosmic events. Astronomers usually figure out what these events are by analyzing their duration, frequency, source, and the specific combination of wavelengths they emit. Here, I just have to say a few words about the instrument that discovered the space anomaly. The Einstein Probe is an X-ray space telescope project led by the Chinese Academy of Science in collaboration with the European Space Agency and the Max Planck Institute for Extraterrestrial Physics. That's a mouthful. This project is all about studying high-energy space events over time. Its main goal is to find inactive black holes and figure out how matter falls into them by spotting X-ray flares produced by these sudden space events. The Einstein Probe also hopes to catch the electromagnetic signals from events that cause gravitational waves, like when neutron stars merge. It also keeps an eye on the whole sky to spot all kinds of space explosions and track already known changing X-ray sources. After the Einstein Probe detected that ultra-bright space flash, the event was also observed by a few other ground-based and space telescopes, including the Nuclear Spectroscopic Telescope Array, SWIFT, Gemini, Keck, Dark Energy Camera, Very Large Array, Australia Telescope Compact Array, and Neutron Star Interior Composition Explorer. That's a bigger mouthful. Using all this data, astronomers pieced together the event's characteristics, but it didn't make the case any clearer. Quite the opposite. It just deepened the mystery. This event flared up in soft X-rays for the first 10 seconds, then plateaued at a steady glow for about 4 days before fading quickly within another day. This is much longer than typical gamma-ray bursts, which usually last from a few milliseconds to several hours. But it was still not long enough to fit into other known categories. The event's brightness in X-rays was also unusual. It was too bright for some types of phenomenon, but not bright enough for others. The most puzzling part is that the Very Large Array didn't detect any radio emission from the source when it was observed 11 days, 158 days, and 258 days after the initial flare. Now normally, when something this bright in X-rays lasts for this long, it's usually associated with a luminous radio counterpart. But in this case, no radio signals were detected, which is very strange and adds to the mystery. Astronomers didn't give up and considered several other possibilities, like fast blue optical transients. Those are a new class of explosions that release huge amounts of energy and blast matter into space at incredibly high speeds. These bursts are so powerful that one F-bot can be at least 10 times more powerful than a regular supernova. Fast blue optical transients do look like supernova explosions, but they are much faster. They flare up and fade away much more quickly than regular supernova. They're also much hotter, which makes the light seem bluer compared to other supernova. Since these explosions happen so quickly, it's tough to figure out what causes them. In January 2019, astronomers narrowed it down to two causes: a black hole consuming a white dwarf star, or a rare kind of supernova that leads to the formation of a neutron star or a black hole. Now, another explanation for our mysterious space explosion, and astronomers think it's the most likely one, is a tidal disruption event. It happens when a black hole swallows a star, causing a flash of light. When a star gets too close to a supermassive black hole, it doesn't get off easily. No, the black hole's powerful tidal forces tear the star apart, breaking it into pieces and pulling it toward the black hole. Its remains turn into a stream of debris that falls toward the black hole's accretion disk. However, before the debris settles into the disk, it overshoots the black hole in an elliptical path, only to be pulled back in. At one point in this path, the debris collides violently with other parts of the star being pulled in, and that's when we start to see the first bursts of emissions. In some rare cases, tidal disruption events create huge jets of material that shoot out from the black hole's poles. If these jets happen to point directly at Earth, we can see the signature of the event. It often looks like an intermediate mass black hole eating a white dwarf star. However, there should still be some radio emissions coming from the jet of a tidal disruption event. The reason none have been detected yet might be that the event was likely observed too early. Previous studies suggest that it can take hundreds or even thousands of days for the jet material to slow down enough to start sending out radio signals. If future observations pick up radio emissions, it could help solve the mystery. But if there are no signals, it might mean it's a very unusual gamma ray burst or something completely new that we haven't seen before. Psst, a giant is hiding in the sky. Kipu is the biggest thing we've ever found in the nearby universe. It's been messing with our understanding of the universe for years, and we've just discovered it. Kipu is dense, powerful, and dangerous to ignore. If we don't understand structures like this, we might be reading the universe completely wrong. So, what exactly is it? It's not a solid object like a planet or a star, and it's not a single thing. It's a superstructure, basically an entire region of the universe, a tangled mess of matter spanning a huge amount of space stitched together by gravity. Kipu is made up of an enormous web of galaxies, galaxy clusters or giant groups of galaxies, gas and dark matter. It's like a superhighway, with galaxy clusters being the cities, filaments being the roads, and dark matter being the invisible infrastructure holding it all together. This giant stretches across 1.3 billion light-years. That means if you traveled at the speed of light, it would still take you 1,003,000,000 years just to cross it. Kipu also holds 200 quadrillion solar masses, even though it only takes up 13% of the observable universe. The name Kipu comes from the Incan system of knotted cords used to record things, called quipus. It was like a writing system. In that system, each knot, color, and twist told a story: numbers, taxes, harvests, and so on. So, when astronomers saw this colossal structure in space, long, tangled, and branching like space cords, they named it after this language of knots. Plus, the shape of the space reminded scientists of those threads. There's a long central filament, and the smaller ones are branching off the sides. What's even more fascinating, Kipu isn't alone. When scientists mapped this part of the universe, they found 5 of these massive structures. They aren't just sitting there either. They formed over billions of years through gravity slowly pulling matter together. All told, all those giants hold nearly half of all the galaxy clusters in that region, 30% of all the galaxies, and a quarter of all the matter in the observable universe. The team that found Kipu used a clever trick. They searched for X-rays coming from galaxy clusters. These clusters aren't just full of galaxies, they're also filled with superhot gas. That gas is so hot it glows in X-ray light, which we can't see with our eyes, but special telescopes can. If there's a lot of that X-ray glow, it means there's a huge amount of matter, galaxies, gas, and dark matter all pulled together by gravity. That's where the densest, most crowded areas of the universe are. So, by following the X-ray glow, the scientists could draw a map showing where the biggest cosmic structures like Kipu were hiding. Why does any of this matter? Because these megastructures mess with everything. First of all, they warp the cosmic microwave background, the ancient light left over from the Big Bang. It's a faint glow of light that fills the entire universe. After the Big Bang happened and our world was created, it emitted its very first light and signals that still haven't completely weakened yet. The leftover radiation is still coming to us, even after 13.8 billion years. By studying this ancient light, scientists can learn what the early universe looked like, and Kipu ruins it for us. These megastructures hold so much gravity that they bend and distort this ancient light as it passes through them. That's called the integrated Sachs-Wolf effect. These warps add noise to the original signal, and now it's harder for us to get a proper, clearer understanding of what the baby universe looked like and how it expanded. They also mess with the Hubble constant. The universe is constantly expanding, and the Hubble constant tells us how fast it's growing. In other words, how quickly galaxies are moving apart from each other. But giant things in space, like Kipu, have so much gravity that they pull nearby galaxies toward them, messing up the way those galaxies move. This makes it harder for scientists to measure the universe's true speed of expansion. They can't tell if a galaxy is moving because of the universe growing or just because it's being pulled by something huge nearby. And finally, there's gravitational lensing. Light in space travels constantly, but it doesn't always follow a straight line. If the space gets distorted, like by gravity, then the light traveling through the space will get bent and distorted too. Gravitational lensing is when light from faraway galaxies gets bent because it passes by something supermassive, like Kipu here. That huge gravity pulls on the light, like how a heavy ball can bend a sheet. And since light delivers information to us, literally makes us see what things look like, this bending distorts how we see galaxies. The images of galaxies end up looking stretched, brighter, or we can even find an entire galaxy in the wrong place. It's like looking at our universe through a warped magnifying glass. If we're not careful, we could misread those distortions and get the wrong idea about what our world looks like. Luckily, we didn't just drop these mysterious superstructures out of nowhere. Astronomers suspected that something like that should be out there. They just didn't know for sure. Our best model for the universe is called Lambda CDM. It says, universe started with the Big Bang, is still expanding, and is mostly made of mysterious stuff, dark energy, and cold dark matter, the CDM part. We can't see or touch these things, but we know they exist, because if they didn't, our universe would literally break apart. This model matches what we do see, like galaxies forming, how stars move, and the overall shape of the universe. So even if some puzzle pieces by themselves are still a mystery, they match the actual picture. And this model actually predicted things like Kipu. When scientists ran simulations using that model, they saw similar structures forming, giant cosmic webs of galaxies tied together by gravity. Kipu matched those predictions in real life. This also means that Lambda CDM is matching real life once again, thank heavens. No huge surprises here. But now that we actually found it, it's the largest known structure in the observable universe. There was another giant before Kipu, the Sloan Great Wall. That one was discovered in 2003 and was believed to be one of the largest structures ever found. And it's still an absolute monster. The Sloan Great Wall stretches over 1 billion light-years across. It's called a wall, but it's not like a wall you'd find on Earth. It's also a vast cosmic web, made up of thousands of galaxies and gas connected by dark matter. What makes both Kipu and the Sloan Great Wall so surprising is that they literally seem too big to exist. According to the Lambda CDM model, structures that huge shouldn't be common, especially at the time they formed. How did these giants form so fast in a universe that's supposed to be growing, expanding, and smoothing over time? And if we keep finding more of them, that would be completely insane. It could mean there's something deeper going on in the way our world is built. It's all part of our crazy Copernican journey, a long series of discoveries where we just keep getting humbled by the universe. Every time we find something like this, we realize even more how we're not the center of everything. First, we learned the Earth wasn't the center of the solar system. Then we found that the solar system is just one speck in a galaxy. Now, even galaxy superclusters, which we believe to be the biggest, are being dwarfed by structures like Kipu and the Sloan Great Wall. But also, these structures won't last forever. Kipu is temporary. Over billions of years, gravity will tear it apart, breaking it into smaller pieces. Some parts will collapse into tighter clusters, others will drift apart. Right now, though, it's one of the most important structures in the known universe. It shapes how galaxies form. It bends light, making it super important for us to decipher. It literally messes with our understanding of the cosmos.
We almost know what happened right after the Big Bang. Scientists understand the universe really well from about a trillionth of a second after it all started. But what about before that? That's where everything gets fuzzy. First of all, we need to remember that our universe is constantly expanding. You can imagine such expansion as inflating a balloon. We know the equations that describe the expansion of the universe. These are the equations of Einstein's general relativity theory. They state that the presence of matter in the universe leads to its expansion. And just like a balloon is inflated at different speeds by hot and cold air, the speed and character of expansion of the universe depends on what type of matter dominates. Slow particles, hot relativistic matter, or even mysterious dark energy. So if you imagine his expansion as galaxies just flying away from an explosion, you need to rethink it. By the way, the Big Bang wasn't actually an explosion, so instead, space itself is expanding, pulling galaxies along with it, kind of like corks floating in a stream. This movement is what we call the cosmic flow. Space is like an elastic medium that stretches, carrying everything with it. Physicist John Archibald Wheeler found a great way of describing it. Matter tells space how to bend, and space tells matter how to move. Basically, the stuff in the universe and space itself are in constant interaction. In general, expansion is an important property of the universe from the very beginning. But how do scientists study what happened to the universe billions of years ago? We cannot look directly into the past. Fortunately, there are indirect ways. When the life of the universe began, it was almost homogeneous, and galaxies appeared from small unevenness. In other words, the distribution of galaxies in the universe shows us the unevenness of matter in the early universe. Another super useful tool is cosmic microwave background spectrum analysis. Let me explain where it came from. At first, the universe consisted of plasma, which is charged particles. Light cannot spread through such a substance because light is scattered by charged particles. It's similar to when we are running through a forest. We have to dodge trees. At some moment, positive and negative charges united, and the universe became electrically neutral. After that, light particles could easily move through it because they had nothing to scatter from. It's as if you were running across a field and not through a forest. So the radiation that was at the moment when the universe became electrically neutral reaches us without problems. It's as if we have a photograph of the early universe. This is a real treasure trove for scientists. Now, when physicists don't have enough data, they use models to make educated guesses. Because in addition to the cosmic microwave background and the distribution of galaxies, there are other indirect observations of various stages of the evolution of the universe. And those different models physicists study must pass all these numerous tests to describe the observables. Then, if we have a model that describes the evolution of the universe, we can use it to understand not only how the evolution of the universe occurs, but also to look into the past. What was its state in the earliest stages? Well, things were extreme. The universe was small, matter was squeezed, and the temperature and pressure were sky high. Go back far enough and you'll hit a point where everything is just a super hot, primordial soup of elementary particles zooming around and smashing into each other. At the time, atoms didn't even exist yet. Even more exciting, today's observations predict that even earlier, there was a stage of very, very rapid expansion. Almost instantly, the universe expanded many, many times. Such fast expansion is called inflation, and it might explain a few big mysteries that cosmologists struggle with. For example, why the geometry of the universe is so perfectly flat instead of curved. Then, there's the horizon problem. How is it that the temperature of the cosmic microwave background, the afterglow of the Big Bang, is almost exactly the same no matter where you look in the sky? And finally, it can help us understand what caused the first tiny clumps of matter, which eventually led to galaxies, stars, and planets to form. Inflation solves these problems because the rapid expansion it proposes would have smoothed everything out, explaining the universe's flatness and even temperature, while also allowing tiny quantum fluctuations to seed the first galaxies. But scientists are still working with other models and theories. So while this idea answers some questions, it doesn't give us the whole picture. There's still much we don't know. But by exploring this and other theories, we're getting closer to understanding how everything began. As we have already found out, the presence of energy in the universe leads to its expansion, and for the expansion to be so fast, a lot of energy is needed. And apparently, this energy came from some unknown field. We know that there might be new forces or particles that only show up at super high energies, but we haven't found them yet. This is where the inflaton field idea comes in. It's the most popular theory to explain the early universe. The inflaton is a field that might have caused the universe to expand incredibly fast in an event called cosmic inflation. Where could this field come from? The standard model of particle physics says there are 12 basic particles of matter, 6 quarks and 6 leptons. The most famous are the up and down quarks, which make up protons and neutrons, and the electron. All the elements in the universe are made of just these 3 kinds of particles. And then we've got the Higgs boson, which gives particles their mass. The amazing thing is that this particle model explains what the universe was made of in its first trillionth of a second, after the Big Bang. But naturally, we want to go even further back closer to the actual Big Bang moment. Unfortunately, or perhaps fortunately, we can't recreate the crazy high energies that existed at the start of the universe in any experiment. We have tested our particle physics theory, only up to the energies that the Large Hadron Collider produces. What happens at higher energies, we can only guess. So scientists have to build their ideas based on what we know. They use the theories of quantum fields to imagine what could have happened at those extreme energy levels. It's not random guessing, though. These theories help us figure out how particles would behave at higher and higher energies. Perhaps one day, our particle physics will be supplemented with new particles that are responsible for inflation. What if dark matter doesn't exist? And what if the universe is way older than we thought? Like 27 billion years old instead of a mere 13.8? It sounds insane, but that's what one scientist is saying. But first off, you know how the universe is mostly made up of stuff we can't see. We do have normal matter, like planets, stars, and whatnot. And then there's dark matter and dark energy. They are supposed to make up most of the universe. Well, Rajendra Gupta, a physics professor from the University of Ottawa, is saying, folks, maybe we don't really need dark matter or dark energy to explain the universe. Let's have a look at his theory. So, Gupta has been mixing up 2 big ideas. One is called tired light, and the other is called CCC, which stands for covariant coupling constants. But we'll just call it CCC from now on. Normally we think that things like the speed of light or the charge of an electron are set in stone. But what if these so-called constants actually change over time? That's the CCC part of Gupta's theory. Then there's the tired light thing. When we look at distant galaxies, the light we see is stretched out and redshifted. Most people explain that by saying that the universe is expanding. But Gupta's idea is, what if light just gets tired as it travels long distances and simply loses energy? These 2 ideas can potentially explain how the universe works, and you don't need dark matter or dark energy to fill in the gaps. But why do people even believe in dark matter altogether? A quick backstory. Back in the 1930s, astronomer Fritz Zwicky noticed that galaxies were moving in weird ways that didn't match up with what we could see. So he thought there must be some invisible stuff out there pulling on everything, what we now call dark matter. And since then, scientists have found more clues confirming this theory, like the fact that galaxies spin way faster than they should if we were just counting visible matter. So most scientists think dark matter is like this invisible glue holding galaxies together, making up about 27% of the universe. Well, Gupta disagrees. He also claims that the universe is actually almost twice as old as we think. According to him, the expansion of the universe isn't driven by dark energy either. It's just that the forces of nature are getting weaker over time. He also focuses a lot on redshift, the way light stretches and gets redder as it travels through space. The scientist believes that when we look at the way galaxies are spread out and compare stuff in the old universe to what we see now, the data actually works without needing dark matter to explain it. If Gupta's theory was correct, it would flip everything we know on its head. It could even explain things like how galaxies formed and what the Big Bang really was. We could even figure out more about that leftover glow from the early universe, the cosmic microwave background radiation. But unfortunately, his idea is kinda outdated. Most scientists are sure there's a lot of evidence for dark matter and dark energy, so Gupta would need to find some really solid proof to convince people. Plus, scientists are working on different theories these days. They're measuring cosmic radiation, examining distant stars, and digging through tons of data to see which theory might be correct. More and more powerful telescopes pop up all the time. So we might actually get some answers pretty soon, and most likely they won't involve tired light. The standard model physics is our best explanation of how tiny particles and forces work. But sadly, it doesn't show us the full story. There are still some great mysteries it just doesn't solve, like why we have gravity, what dark matter is, and why there's so much more matter than antimatter in the universe. Plus, the standard model doesn't work with Einstein's theory of gravity, which makes things weird near black holes or the Big Bang. What I mean is the standard model doesn't explain gravity, which is actually a massive deal. We can't just toss in a graviton particle and call it a day because this model and Einstein's gravity don't get along. They each work great on their own, but not together, especially in extreme spots like black holes or at the start of the universe. Right now, particles are seen as tiny excitations in fields, known as quanta, described by quantum field theory. But calculations often produce nonsensical infinities. To handle this, we replace these infinities with measurable values, making the theory work in the real world. This process is called renormalization. When it comes to gravity, though, things get complicated. Trying the same method for gravity leads to an infinite number of these infinities, requiring endless experiments to fix them, which is an impossible task. This makes gravity non-renormalizable, so we can't fit a gravity particle or graviton into the standard model. Then, we should remember that particles behave differently depending on their energy level. To study them at higher energies, we first have to accelerate them to those levels. Right now, the highest particle energies we can reach are at CERN. So, the standard model is mainly designed to explain what we see in experiments there, but we can't be sure it holds true at even higher energies. In fact, there are clues suggesting that the standard model might start to break down beyond the energies we can currently achieve. Plus, the standard model explains around 5% of the universe's stuff. What about the other 95%? That's where dark matter and dark energy come in. Dark matter behaves like normal matter, but is totally invisible, while dark energy acts like a mysterious anti-gravity force, pushing the universe to expand faster. Then we have neutrinos. They should have no mass according to the standard model, but they actually change types or oscillate in a way that suggests that they do have mass. Scientists simplified things by setting neutrino mass to 0 in the model. And this doesn't impact CERN's results since neutrino masses are extremely small. Finally, our universe is made mostly of matter, yet the standard model says that matter and antimatter should have been created equally. So why don't we have a balanced mix of both? Scientists call these gaps beyond the standard model physics. We'll call it BSM physics. This is where things get exciting because physicists are exploring all sorts of ways to expand the standard model with ideas like new exotic particles or hidden forces we haven't discovered yet. And recently, CERN's NA62 experiment has announced a big discovery that might help us finally find BSM physics. They observed a super rare kaon decay where a positively charged kaon decays into a pion and a neutrino-antineutrino pair. How rare is this process? It happens in less than 1 in 10 billion kaon decays. This level of rarity makes it the perfect place to search for even the smallest deviations from the standard model predictions. This process had been seen before in past experiments. But this time, Na62 hit the 5 sigma mark. It's a level of certainty that's considered a real discovery in physics. But why is this kaon decay so important? Physicists track rare decays because they act like sensitive detectors for hidden physics. The standard model makes specific predictions about how often these decays should occur. If the measured decay rate doesn't match the predictions of this model, that's a big clue there could be some hidden physics lurking in the background. Na62's latest measurement of the kaon decay rate was about 50% higher than what the standard model predicts. This difference is still within the margin of error, but raises an eyebrow or two. Obviously, more data from the experiment will help clarify whether this difference means new physics or just random chance. By the way, making this discovery wasn't easy. The Na62 team created kaons by blasting a high-intensity proton beam into a stationary target, generating nearly 1 billion secondary particles per second. Out of these, around 6% were positively charged kaons. The researchers carefully tracked those kaons with their detector to record the decay products. From 2016 to 2022, Na62 collected data and upgraded its detector, boosting its beam intensity by 30%. Such upgrades were crucial. They helped with filtering out background noise and distinguishing those ultra-rare decays from the billions of others. With more data rolling in, Na62 hopes to push the boundaries even further. Physicists are excited to see if this kaon decay might really be hiding some BSM physics. It's all about spotting tiny blips that hint at something new and groundbreaking in the universe. Traveling in time appeared in many sci-fi movies, but every law of physics claims that the only way we can move through time is forward. Well, thanks to some very exciting properties of space and time in Einstein's general relativity, going back in time seems to be possible after all. According to Einstein, space and time are not separate entities. They're woven together in the fabric of space-time. There's also a quantity that generalizes the concept of distance into 4 dimensions, the space-time interval. It takes into account distance in time. In other words, if you're resting, your spatial position doesn't change, and you're moving through time forward at 1 second per second. But if you're moving, and your spatial position changes, you travel through time more slowly. All because objects in relative motion experience something known as time dilation. Roughly speaking, the faster you travel through space, the more slowly you move through time. More precisely, time dilation is the difference in elapsed time as measured by 2 clocks because of a relative velocity between them. The faster the relative velocity, the greater the time dilation between them, with time slowing to a stop as 1 clock approaches the speed of light. However, keep in mind that we only know about massless objects, such as photons, that travel at the speed of light. Theoretically, if you could move faster than the speed of light, you'd become a tachyon, a hypothetical particle that always travels faster than light. Also, there is the energy-momentum relation that connects energy, momentum, and mass. One can see from that relation that if a particle moves faster than speed of light, then its mass is imaginary. So, this possibility is an unphysical situation, since tachyons don't correspond to anything that exists in our physical reality. However, Einstein thought that going faster than the speed of light wasn't the only way to travel backward in time. Space-time might not be flat and unchanging. It can be curved, can contract and expand, and can even create and maintain a connection between 2 different points within it. This possibility is known as an Einstein-Rosen bridge. If you jumped into one point and your friend jumped into the other, you could meet somewhere in the middle. At the same time, this tunnel wouldn't be passed through, and you wouldn't be able to get out on the other side. Now, try to imagine space-time as a 2-dimensional sheet of paper. If you fold it, 2 points that were previously separated will become connected in this new 2-dimensional world. This property of space-time might be the most important concept of time travel. You probably know this concept under the name of a wormhole. And it's tightly linked to black holes, regions of space containing so much matter and energy that any light emitted from that region, as well as any matter and radiation that falls there, will never escape. And it doesn't matter how much energy it has or how fast it's moving, even if it's the speed of light. Usually, it's assumed that black holes only lead to a central singularity, and if you fall behind the event horizon, also known as the point of no return, there is nothing but destruction awaiting you. But how about another possibility? What if black holes could actually transport you to another universe? Then, you would be expelled on the other side through something called a white hole, a time-reversed solution of a black hole. But so far, all this sci-fi theory is just a hypothesis. What we do know is that minuscule quantum fluctuations exist in our known universe. They occur throughout the fabric of space-time, most prominently on the tiniest of scales. Such energy fluctuations can occur very close to one another. They are most likely random and often include disconnections and reconnections from the original positive and negative states that initially occur together. If you somehow connected such positive and negative curvature regions together, you could get close to the notion of a quantum wormhole. And if such a wormhole remained intact for a long enough period of time, you could transport a particle through it. In other words, it'd instantly disappear from one location in space-time and reappear in another. But why is a wormhole so crucial when we talk about time travel? Because once you create two ends of a wormhole and maintain the connection between them with sufficient mass and energy, this connection will remain eternally. And since this is great for instantaneous travel through space, probably we could extend it to traveling through time too. Sadly, at the moment, it's just wishful thinking.
Long before satellite TV or GPS, NASA made a huge silver balloon to show that global communication via satellite was possible. This was ECHO, the U.S. first communications satellite. We can say that it paved the way for many current communication technologies. It all started when scientists realized that we already had a satellite that could reflect signals. Right, I'm talking about the moon. After a series of tests, they successfully used Earth's natural satellite as a huge reflector to send voice signals from California to New Jersey. They even established a two-way telephone line using the moon as a reflector. But how was it possible? Often in underground car parks or even outside, mirrors are installed at turns with poor visibility. It's an easy way to look around corners. Fundamentally, the same idea has been used for almost the entire history of wireless signal transmission over long distances. Imagine you want to send a signal from one point on the planet to another point on the other side of the globe. The direct signal cannot travel this way. Therefore, you need some mirror, but high in the sky. At first, people used the upper layers of the atmosphere for reflection, but this is tricky and requires a lot of effort. Therefore, scientists decided, why not launch an artificial mirror into orbit? Because just like light bounces off a mirror, radio waves can be reflected too. When some signal bounces off a surface, it spreads out in all directions. A small portion of this signal is bound to make its way back to Earth, and there, it can be picked up by a receiver in a different place. The larger the reflector is, the stronger and more focused signal it will return. But let's get back to ECHO. Originally, it wasn't designed to be a communication satellite. Engineers first thought of the balloon as an air density experiment. They believed that the ways to measure air density in the upper atmosphere were insufficient at that time. So they designed a better craft. But later, due to some circumstances, Project ECHO turned into a communication relay. Technologically, ECHO was rather simple, and it functioned as an enormous mirror in orbit. But to work, it had to be supermassive. ECHO 1 was made from a huge sheet of mylar plastic. It was incredibly thin, a mere 1/10 the thickness of a human hair. The sheet itself was cut into more than 100 gores, and each of them was covered with a thin layer of aluminum. That's what gave the balloon its shiny appearance. After that, the gores were glued together, creating the final sphere. Once it was finished, NASA inflated Echo for the first time. The huge balloon came to life in 1958. It was one of the largest things ever launched into space, and the only way to send it into space was to pack it down and inflate it once it was in orbit, and it turned out much more challenging than one could think. Instead of carrying its own air, Echo had small canisters with benzoic acid. That's a special powder that turns directly from a solid to a gas when heated. So when the balloon was released into space, the heat from the sun turned the powder into gas in no time. It all expanded inside the balloon, and in a matter of seconds it was fully inflated. Such a massive object floating in space made it a target for micrometeorites. To protect the balloon from small punctures, engineers supplied it with an extra amount of benzoic acid. It could be released to maintain the balloon's pressure. Echo 2, though, had an even better solution. Its skin was made of mylar too, but it was sandwiched between two huge sheets of aluminum foil. When the balloon was pressurized, the foil stretched, stiffening and hardening in place. It made the balloon become rigid without any additional internal pressure to maintain its shape. Even if micrometeorites hit it, it could still hold its shape. No wonder these giant, shiny things were very visible. For a decade, they were some of the brightest objects in the sky, brighter than the North Star. And this brightness was the key feature of the balloon's design. To send and receive signals, the ground stations had to be able to track the balloons as they moved across the sky. The easiest way was to point the antenna dish directly at the balloons once they were visible. But it was only possible during twilight hours when the sun was illuminating them. When the balloons couldn't be spotted with the unaided eye, they relied on NASA's tracking network, predicting the orbits of the satellites. On Echo 2, there was a tracking beacon. It sent out pulses, which made the balloon easier to track during the day. Most of the project's communication was done between special ground stations in New Jersey and California. At the same time, Echo was supposed to be a global experiment. Thanks to their orbits, the balloons flew over every part of the planet. It allowed transmissions to be done literally anywhere by anyone who had the necessary equipment. One of the cool things about the balloons was that they weren't only used for sending signals around the world. They also helped researchers to accurately measure the shape and size of our planet. You see, at that time, the most accurate measurements relied on a method called star triangulation, and the actual distances between cities and continents could be off by more than 100 miles. So researchers used Echo to figure out the exact location of different points all around the globe. They measured the time a signal needed to travel from two locations, which gave them the precise distance to Echo. After that, by measuring the angle at which Echo appeared in the sky, scientists formed a triangle, being able to calculate the distance between 2 points to within several feet. It made all the calculations 10 times more precise. At that time, though, NASA was still a very young organization, so people working there knew very little about the long-term effects satellites experienced in space. And one of the biggest unknown factors was atmospheric drag. Even at really high altitudes, like 1,000 miles and more, there are tiny traces of atmosphere that can slow down objects. Imagine trying to walk through waist-deep water. The water will resist your movements and make it harder to move forward. The same happens with spacecraft. They push on the air, and the air pushes back in the opposite direction. The denser the atmosphere a spacecraft is traveling through, the greater amount of drag it experiences. It allows researchers to estimate atmospheric density by measuring how drag changes the orbit of a satellite. Echo's had a large surface area to mass ratio, so the balloons felt the effects of drag more than any other satellite. Observing Echo 1, NASA managed to track how its orbit changed over a few years, and it was a lot. Strangely, it wasn't atmospheric drag that had altered it. Solar wind radiating from the sun was to blame. It was pushing Echo 1 toward Earth. The balloons kept working perfectly well throughout the 60s. They proved that a global communication system in space was possible. Plus, They gave rise to many new techniques and technologies. For example, the first balloons spawned other satelloons, a combination of satellites and balloons. Echo 2 also fulfilled the original purpose of measuring air density and solar radiation. Echos's metallized plastic helped scientists evaluate the use and long-term durability of similar materials for other spacecraft. By the mid-60s, active communication satellites had become a more effective solution than passive systems like Echo. With the help of a passive system, the transmitted signal had to be strong enough to travel all the way into orbit and back. And with an active system, the signal only needs to be strong enough to travel all the way up there to the satellite, which then gives it power for the return trip. In any case, during their mission, the iconic balloons showed us even more than we could have imagined. Afterward, the receiver that was used to detect Echo's signals continued its work, as well as other materials used for the Echo project. They are still used in different spacecraft. It is assumed that there is a supermassive black hole at the center of every galaxy in our universe. These space monsters have been discovered in the centers of many galaxies, and our Milky Way is no exception. There is Sagittarius A at its center, a supermassive black hole surrounded by a hot, radio-emitting, accreting gas cloud. To accrete means to absorb matter from the surrounding space under the influence of gravitational forces. In the case of black holes, the attraction is incredibly strong. As a result, the radiation surrounding them is also immensely powerful. Observations made by the Event Horizon Telescope in 2022 made it possible to simulate this substance in our galaxy. From these observations, astronomers were able to estimate the mass of the black hole. It turned out to be 1 million solar masses, which is about 1 million times less than the mass of the entire Milky Way galaxy. So, 1/1,000,000th of the mass of our galaxy is that supermassive black hole at its center. Such a ratio of the mass of the entire galaxy to the mass of the black hole at its center is characteristic of many observations. Moreover, the value of this ratio is reproduced within the framework of modern models. Now, let's discuss two hypotheses for the formation of supermassive black holes. The first model speaks about the creation of small seeds that describe the gradual increase in the mass of a black hole, the accretion of matter into a stellar mass black hole. The second model suggests that supermassive black holes form when large gas clouds collapse. In this case, the collapse occurs bypassing the stage of a supernova explosion, in which the explosion would scatter most of the mass, preventing the formation of a supermassive black hole. In any case, conceptually, such a process can be described this way. There's matter in some compact area, which is the seed for the growth and development of a black hole. Black holes accrete matter around them and their mass increases. It is important that the evolution of black holes is a temporary process that scientists want to study in dynamics. But how can one see evolution that takes place over millions or even billions of years? Unfortunately, or fortunately, light from a distant galaxy takes time to reach us. That's why if we look at very distant objects, we will see them as they were in the past due to the propagation delay of light. But to look far into the past, one needs to look at very distant objects. The light from them is very difficult to observe experimentally. The good news is that with the launch of the ultra-precise James Webb Space Telescope, scientists can study even faint signals from galaxies that formed when the universe was about 1 billion years old. That is, looking back almost 14 billion years. One of the most surprising results obtained from James Webb is the discovery of a lot of galaxies within 2 billion years of life of the universe. These galaxies have active galactic nuclei, faint compact regions at the centers of galaxies, emitting large amounts of energy. Here, the Space Telescope shows its power. These active galactic nuclei have luminosity that are thousands of times lower than the luminosity of quasars detected in ground-based studies. They appear red because they are dusty. The dust obscures black holes and reddens the colors, so they're called little red dots. What is very important, their masses lie between 10 and 100 million solar masses. Surprisingly, using very advanced analysis methods, scientists can estimate the mass of a black hole at the center of a little red dot. It turns out that it reaches millions of solar masses. It means that the mass of a black hole at the center of such a little red dot is only several orders of magnitude less than the mass of an entire galaxy. I'll remind you that the supermassive hole at the center of our galaxy is millions of times smaller than the mass of the entire universe. Thus, the ratio of the mass of supermassive black holes at the centers of such galaxies to the mass of the entire galaxy is phenomenally large. But explaining this fact will be a difficult problem for current models of black hole evolution. One of the hypotheses that scientists are now working on is that it's not a black hole that forms from a seed at the center of a galaxy, as we discussed earlier. It's a galaxy that forms around the already created black hole. Such black holes are called primordial black holes. This is a hypothetical type of black hole that was formed not due to the gravitational collapse of a large star, but in superdense matter during the initial expansion of the universe. If it turns out that these primordial black holes do exist, it will open up a new window for dark matter models. But this is a topic for another video. Recently, an international team of astronomers has used the James Webb Space Telescope to find evidence for an ongoing merger of two galaxies and their massive black holes, and it happened when the universe was a mere 740 million years old. The double black hole system is known as ZS7. This is the most distant detection of a black hole merger ever. Plus, it's the first instance of such a phenomenon detected so early in the universe. But let's look into the details. Astronomers have been locating different supermassive black holes with masses of millions to billions of times the mass of the Sun, situated in the most massive galaxies in the local universe, including our home Milky Way galaxy. Those giant black holes most likely had an immense impact on the evolution of the galaxies where they dwell. At the same time, scientists don't fully understand how those objects got to be so massive. The discovery of such monstrous, fully formed black holes means that their growth occurred very quickly and very early. Massive black holes that are actively accreting matter have special features that allow astronomers to detect them. These features are usually not visible from the ground, but can be observed with the help of James Webb. So, researchers found evidence for very dense gas clouds with rapid motions close to the resulting giant black hole. Plus, they detected hot and highly ionized gas, illuminated by energetic radiation, like the one typically produced by black holes in their accretion periods. With the incredible sharpness of the telescope's imaging capabilities, scientists also managed to spatially separate the two black holes. One of these holes has a mass that is 50 million times the mass of the Sun. The mass of the other black hole is likely to be similar, but it's much more difficult to measure it since this second hole is surrounded by a thick cloud of gas. These findings suggest that mergers are a crucial way through which black holes can grow extremely fast, and they could do it already at cosmic dawn. After analyzing other Webb's findings of active massive black holes in the distant universe, researchers have come to the conclusion that massive black holes have been influencing the evolution of galaxies from the very beginning. Once the two black holes merge completely, they will also generate gravitational waves. Such events are supposed to be detected by the next generation of gravitational wave observatories, such as the upcoming Laser Interferometer Space Antenna, aka LISA, mission. It has been recently approved by the European Space Agency. This mission will be the first space-based observatory dedicated to studying gravitational waves. The results we get from James Webb tell us that lighter systems detectable by LISA might be more frequent than we used to think. It will likely make researchers adjust their models for LISA rates in a similar mass range. Currently, astronomers are planning to study in detail the relationship between massive black holes and their host galaxies in the first billion years. An important part of this program is systematic search for and characterization of black hole mergers. It will help us determine the rate at which black hole merging occurs in the early universe. Plus, with the help of this research, we can figure out the rate at which gravitational waves have been produced from the dawn of time.
Our home Milky Way galaxy has two very well-known satellite galaxies, the Large and Small Magellanic Clouds. They were named after Ferdinand Magellan, an explorer who led the first circumnavigation of the globe a whopping 500 years ago. During this expedition, two groups of clouds were discovered in the southern night sky. Those are now known as the Magellanic Clouds. But they're not the only ones. The Milky Way is surrounded by at least 61 other galaxies within 1.4 million light-years. For comparison, our neighbor, the Andromeda Galaxy, is 2.5 million light-years away from us. And still, astronomers think there are many more satellite galaxies, perhaps even too many. But first, let's figure out what a satellite galaxy is. Our Sun is just one of a truly huge collection of stars in the Milky Way. Hundreds of billions of stars orbit the center of our galaxy. But something much bigger orbits the Milky Way's center too: other galaxies. They are way less massive, but have their own stars. We can compare the Milky Way to our Sun, and those other galaxies to planets. Astronomers call such formations satellite galaxies. The Milky Way's biggest satellite galaxy is the Large Magellanic Cloud. It's located about 163,000 light-years away and is about 1/100th the size of our home galaxy. Unlike the spiral Milky Way, the Large Magellanic Cloud doesn't have a clean spiral shape. One theory claims that it's because the Milky Way and other galaxies pull and warp it. In terms of distance, there are two candidates that can fight for the title of the closest satellite galaxy. One of them is so small that scientists consider it a dwarf galaxy. The other is so close that it's still debated whether it's a separate dwarf galaxy or part of our own galaxy. The satellite galaxy everyone agrees on is the Sagittarius dwarf spheroidal galaxy. It's around 50,000 light-years away from the center of the Milky Way. But there's a cluster of stars that is even closer than that. Some experts call it the Canis Major Dwarf Galaxy. It's likely to contain about 1 billion stars and is located so close to the edge of the Milky Way that it's actually closer to our solar system than to the galaxy's center. Some astronomers don't think the Canis Major is its own galaxy. They believe it's simply a dense area of faraway stars, which is still part of the Milky Way. Whatever the case is, this bunch of stars was once pulled toward the Milky Way by our galaxy's immense gravity. That's how most satellite galaxies in the area are likely to end up. Once, they might all merge into an even larger Milky Way galaxy. But let's get back to the assumption that the Milky Way has too many satellite galaxies. A team of astronomers has been hunting for such galaxies using the Subaru telescope. So far, they have searched a mere 3% of the sky. And still, they have found 9 previously undiscovered satellite galaxies. That's far more than they expected to spot. Interestingly, most of the satellite galaxies orbiting the Milky Way are newcomers. Yes, even the Large and Small Magellanic Clouds. This most recent research hopes to improve our understanding of our corner of the universe with the first detailed search for companion dwarf galaxies. However, the study also has another goal: to figure out dark matter distribution. You see, the current theory claims that the mass of our galaxy consists of 2 parts: visible matter, like stars and planets, and something invisible, which is hypothetical dark matter. We can't see it directly, but we can feel its gravitational influence through a certain distribution of mass in galaxies. Strangely, the simulation of the dynamics of the galaxy and this dark matter predicts hundreds of satellite galaxies in the Milky Way. Until recently, we only knew about a few of them, which created a contradiction known as the missing satellite problem. Hopefully, the new research will solve this problem. The team admits that so far their research has been based on statistically small numbers. Several assumptions have also been made based on a particular distribution of satellite galaxies. Follow-up studies of stars in the satellite galaxies and high-resolution imaging are definitely needed to progress further.
It's 2065, and you're standing on the moon's dusty surface, working away on the latest array of solar panels to help fuel the local town's energy grid. Suddenly, the surface begins to shake. Is this a moonquake? Or are those moon-born teenagers having a party in the town hall again? You look up at Earth. You're so used to it, you barely even notice it anymore. But now, it looks different. It takes you a few moments to work out why. It appears to be shrinking. You begin to panic. The Earth is moving away. The ground rumbles again, and you work out what's happening. The Earth isn't moving, but what you're standing on is. The moon has broken off its orbit and it's heading out into deep space. Destination unknown. The strange thing is, it's happening right now, and has been for a very long time. It's even affecting how long our days are. Eventually, it will pull away altogether and dramatically affect our planet's oceans. To explore what will happen, let's go back a little, to put it all into perspective. The moon has been hanging around us, literally, for 4.51 billion years. There are a few theories as to how the moon came into being. The main one is that it formed when a large object smashed into the young Earth. The early solar system was a chaotic place. A number of stellar bodies were created that didn't make it into a full planet. One of these bodies, as large as Mars, smashed into Earth, throwing huge chunks of our planet's crust into space. Gravity took over and tied these separate elements together. This explains why the moon is made of lighter particles than we find here on Earth. Billions of years later, and we're more than used to having the moon with us. It affects so much of our everyday life. The obvious one is tidal motion. The gravitational pull or tidal force that the moon exerts on our planet creates the tides. This force causes all of the water on the Earth's surface that's closest to the moon to bulge out to one side. A very short explanation is that it pushes in from the top of our planet and also the bottom, while pushing out from the sides at the same time. The Earth also has an effect on the moon, which we'll get into in a minute. But it appears that the moon might not like our company as much as we might think. It's slowly drifting away from us, even as we speak. The moon can seem small or large depending on the lunar cycle, but in actuality, it's just over a quarter or 27% of the size of Earth. The diameter of the moon's orbit around us is nearly 477,213 miles, but this diameter is increasing by 1.5 inches every year, which of course means that it's moving away by a factor of 1.5 inches each year. To help explain why we have to analyze our relationship to the moon a bit more closely, both celestial bodies are tidally locked. We are synced up in such a way that we always see the same side of the moon. The hemisphere that we never see is often referred to as the dark side, but that's not quite right. As the moon orbits Earth, different parts are in sunlight or darkness at varying times. This change in illumination is the moon going through its various phases. The tidal forces not only affect our oceans, but the body of the Earth too. Because the Earth is more rigid in structure than water, the tides on more solid matter, like the Earth's crust, have a much smaller effect. The tidal forces are interdependent. The gravitational field of the Earth will also apply tides in the body of the moon. Again, because we're not talking about fluid, the effect is very small, but it's there. This interchange of tides is quite complex. Interiors of both bodies are heated by these tides, just as the force applied to any object can create friction or its own heat. Take the planet Jupiter, for example, and its moon, Io. The tidal forces of the giant planet are so huge that the surface of Io, which is solid, is raised and lowered several hundred feet in each rotational period. The heat generated means that the interior of Io is most likely molten. As a result, the surface of Io is covered with active volcanoes. It's one of the most geologically chaotic places in our solar system. Despite its heat, it's definitely not the place to take the family for a summer holiday. Back to Earth. Our planet rotates on its axis once every 24 hours, and the Moon performs one revolution around us in 27.3 days. The bulge on Earth actually speeds up the Moon. The Earth pulls the Moon ahead in its orbit. In other words, the Earth's bulge increases the radius of the Moon's orbit around us. While this is happening, the Moon pulls back on the tidal bulge of the Earth, slowing its rotational speed, though just a fraction. A very small fraction. This means that 100 years from now, a day on Earth will be 2 milliseconds longer than it is right now. Blink and you'll miss it. Literally. In addition, since the Earth is larger, the gravitational pull is stronger, causing the Moon to speed up slowly. As time passes, its orbit will become bigger and bigger. This takes us back to that measurement of 1.5 inches. It may not seem like a lot, but over a period of time, this measurement becomes significant. Let's jump forwards billions of years from now, where we see that the Moon's orbit is so big that it does leave the pleasure of our company permanently. What happens to our oceans then? You've already guessed it. The tides will cease to be. That will make for very calm seas for any boat trips. That's if there are any humans left in, 50 billion years. Before that time, because of the tidal locking slowing down the Earth's rotational speed, it's possible that the Earth will slow down enough to permanently face the Moon. In turn, it may prevent the Moon from moving away from us. Imagine the effect on our planet if we stop rotating. One half will always be in darkness, the other in light. That'll play havoc on our seasons and the natural life. While it sounds dramatic, and the loss of tides would be a significant phenomenon, there are other more serious things to worry about occurring before then. In a tenth of that time, 5 billion years, our Sun will likely consume both the Moon and the Earth. Yep, our Sun is going to have a galaxy-sized party, the likes of which our solar system has never seen, and everyone's invited. The Sun is continually burning the hydrogen in its core into helium. Right now, it's approximately halfway through its life cycle. Towards the end, it will run out of hydrogen in its core. The Sun will ultimately become a red giant. Its surface is predicted to reach Mars. That's when gravitational forces will take over. The Earth will be dragged into this new Sun and disintegrate. The Sun gets 10% brighter every billion years. So long before the planet is totally destroyed, the heat will have melted any ice and fried almost everything living. All of our oceans will have dried up too. So, while the planet has a 5 billion year life cycle yet, everything living on it may only have a billion. To recap, the Moon may move from the Earth, but the Sun will have wiped out both long before the tides are halted. Let's steer away from that hot object and return to that sibling-like relationship of the Moon and Earth. The fact that the Moon has the same rotational period as the orbital period of both the Earth and the Moon is no coincidence. Over billions of years, the tidal coupling of the two has led to the synchronization we know today, and yet it's still evolving. The Earth is slowing its rotational period. Eventually, it will match that of the Moon, and they will be exact. And as I mentioned before, the days on Earth will become longer as well, by 2 milliseconds every century. To have a significant impact, it will take many thousands of years. However, it's nice to think that both the Earth and the Moon affect each other in many powerful and beneficial ways. It's almost like they're simply hanging out together, like a couple of old intergalactic buddies. Under your feet, the Moon is pulsing. You feel danger with every pore of your body. The lifeless satellite, or so you thought, stay still for a second before knocking you down to the ground with a powerful tremor. Is it a moonquake? For years, scientists believed the moon was completely inactive, but the newest evidence seems to suggest that this idea is totally wrong. Researchers from the University of Maryland have recently discovered 266 mysterious ridges on the far side of the moon. And these ridges likely point to recent geological activity. So, are we really talking moonquakes? Well, kind of. The ridges are located in volcanic regions that formed 3.2 to 3.6 billion years ago, but they appear much younger than expected. Typically found in clusters of 10 to 40, they're often located in areas where the moon's surface is structurally weaker. Now, when astronomers speak about recent, don't take their words literally. They don't mean last year or even decade. Most models scientists created suggested that the moon's geological activity ended 2.5 to 3 billion years ago. But the new information hints at the possibility that these formations have been active within the last billion years. Some of the smaller ridges seem to have formed as recently as 200 million years ago, and that is considered relatively young on the moon's timescale. It means that the moon may still be experiencing geological changes today. These discoveries kinda challenge our understanding of the moon's history and evolution. But how did scientists come to these conclusions anyway? Researchers from the University of Maryland and the Smithsonian Institution used crater counting to estimate the age of lunar ridges. It works like this. Surfaces with fewer craters are younger, and the more craters some region has, the older it is. Plus, the analysis showed that some ridges cut through already existing craters, meaning they likely formed around 160 million years ago. In geological terms, this is very recent, suggesting that these ridge-forming processes may still be happening. Another cool thing is that the ridges on both the near and far sides of the moon are similar, which means they may have formed through the same geological processes, having been shaped by the same forces. These forces might include the moon's gradual shrinking, thermal contraction, and shifts in its orbit. We'll talk about it a bit later. Another argument supporting the idea of a still active moon is decades-old data from the Apollo missions. They had already detected shallow moonquakes with the Apollo Lunar Seismic Experiment, recording 28 quakes ranging from magnitude 1.5 to 5. Researchers believe that these ridges may be linked to similar seismic activity. Now, about that bizarre shrinking of our natural satellite. Scientists believe the moon formed about 4.5 billion years ago when a Mars-sized object collided with early Earth. This catastrophic impact likely sent bunches of superheated material into space. Eventually, they came together and formed the moon. In its early years, the moon was just a molten world, shaking from intense volcanic and seismic activity. So, the moon used to be a molten mess floating through space. But when did it actually solidify? Scientists have finally figured it out, 4.43 billion years ago. This was a huge turning point, not just for the moon, but for Earth too. After all, the giant impact that formed the moon might have also been the final blow that made Earth stable enough to support life. In any case, billions of years passed. The moon gradually cooled and contracted. And now look at this modern-day rocky sphere illuminating our nights. But the moon isn't completely rigid yet. It still keeps cooling. And this slow cooling of its core might be one possible reason for the moon's continued activity. As it cools, the moon's interior contracts, which leads to cracks and shifts in the crust. One of the clearest signs of this contraction is found in the lunar maria. See these large, dark patches on the moon? Those are called maria, areas formed when lava filled ancient asteroid impact craters and then solidified. Then, over time, the cooling and contracting crust created these wrinkle ridges. Another factor of the ongoing geological activity could be the moon's gravitational interactions with Earth. Such non-stop powerful interactions likely create surface stress and trigger tectonic movements. It's all good and exciting, but can this activity on the moon actually affect humans? In a sense, it can. The moon has long been seen as a stable place for future bases and resource extraction. But the discovery of this ongoing geological activity is pretty worrying. If the surface is still shifting, future settlements, infrastructure, and mining operations could face serious risks. That's why, at the moment, we need seismometers and ground-penetrating radars to better understand these movements. It will allow us to assess potential dangers before any long-term missions begin. By the way, there's another potential problem future lunar missions might have to deal with, and it's moon dust, aka regolith. Apollo astronauts quickly learned that this jagged, sticky dust gets everywhere and can damage suits, equipment, and even health. A new study from Texas A&M engineers found another problem. When rockets land or take off, they kick up regolith, which can become a collision hazard, especially with many spacecraft bringing crews and cargo to the moon. Lunar regolith comes in all sizes, from tiny dust particles to large rocks. The main ingredient in moon dust is fine silicate materials, about 70 microns in size, like a human hair. They formed over billions of years as meteors and asteroids smashed into the moon's surface, grinding much of it into powder. Unlike Earth, the moon has almost no atmosphere. It's incredibly thin, so there's no wind or water to smooth out the dust. On top of that, constant exposure to solar wind has given the regolith an electrostatic charge, making it stick to anything it touches. Apollo astronauts quickly found this out the hard way. Moon dust clung to their suits, got trapped inside their landers, and stuck to everything. Worse, it became a health hazard, causing eye irritation and breathing problems inside their spacecraft. But at the moment, it seems like a problem for future us. A much more important issue is finding water to support future missions, and China is going to deal with it. It's getting ready for a big mission to look for hidden ice on the moon. As part of the Chang'e 7 mission in 2026, a flying robot will explore deep craters at the moon's south pole, where ice might be trapped. If they manage to confirm it, this could be a game changer for future lunar missions. Astronauts will have a water source and even fuel for space travel. The mission is a key step in China's plan to land astronauts on the moon within 5 years. While signs of water have been found before, like in soil samples from Chang'e 5's probe and observations by NASA and Indian spacecraft, scientists believe that deep ice deposits are the real key to supporting future missions. The south pole of the moon has some incredibly deep craters, and experts think ice could be hiding inside them. The flying robot will try to explore one or more of these craters after landing. If it does find the ice, it could make long-term moon missions much cheaper and more practical, helping astronauts live and work on the moon. Some scientists also think that this discovery could offer us some clues about extraterrestrial life. In any case, whether we find water on the moon and learn to deal with that pesky dust or not, the recent discovery of those young lunar ridges is a game changer. If the moon is still geologically active, it means we don't know as much about our closest neighbor as we thought. What else could the moon be hiding? Are we really prepared for the idea that this lifeless satellite might actually be more dynamic than we imagined? Future missions, which might not be as safe as we once believed, will probably show. Soon we might start constructing loads of stuff on the moon. All because India's moon mission has recently detected sulfur near the moon's south pole. This chemical element can come in extremely handy for creating infrastructure on our satellite. It's the first time this chemical element has been discovered on Earth's natural satellite. This sought-after element is mostly found near Earth's volcanoes. Its appearance on the moon speaks volumes about the satellite's volcanic history and its past atmospheric conditions. The mission's rover detected this chemical element less than a week after touching down around 70 degrees from the moon's south pole on the 23rd of August, 2023. This historic landing on the lunar surface made India the 4th country to safely land a mission on the moon. It's also the first spacecraft to touch down so close to the south pole of our satellite. It's an area of strategic importance because it's believed to be home to deposits of water ice. If it turns out to be true, future missions might be able to harvest it and turn this water ice into drinking water or even rocket fuel. For 2 weeks, the lander carried out the data collection, mainly focused on the analysis of the moon's soil and its extremely thin atmosphere. Meanwhile, the solar-powered Pragyan rover started its quest to find frozen water on the moon. As for the lander, it demonstrated another amazing feat on the 3rd of September. The spacecraft fired up its engines and lifted itself for about 16 inches into the air. Then it made a tiny hop to land 12 to 16 inches away from its original position. It's kinda a big deal. Being able to get a lander back off the surface of the moon is essentially for future missions, showing that they can safely return soil samples or even astronauts back home after a lunar mission. In September, the Indian spacecraft was put into sleeping mode. The 14-day-long lunar night was approaching, and the spacecraft wasn't designed to collect scientific data during this period of time. So far, we've learned about a few major findings of the mission. One is related to measuring the temperature of the moon's topsoil at different depths. Intriguingly, the surface of the satellite in that region turned out to be hotter than expected. It was believed that the temperature could be between 68 and 86 degrees Fahrenheit on the surface, but it was around 158 degrees Fahrenheit, way hotter than it should be. The other discovery indicates the presence of several chemical elements, including oxygen. Besides, the data received from the spacecraft confirms the presence of aluminum, calcium, iron, titanium, silicon, and other chemical elements on the lunar surface close to the South Pole. The rover also used special instruments designed to measure quakes and rumbles beneath the lunar surface to detect some seismic activity. It brings us back to the sulfur detected thanks to the rover's spectroscope. Scientists are currently working on figuring out whether this element formed on the surface in a natural way or whether it's the result of volcanic activity or a meteor strike. Another astonishing thing found on the moon is a rock, and it may be the oldest known Earth rock. A 0.7-inch wide chip included in a large rock collection brought to our planet by Apollo astronauts might actually be a 4 billion-year-old fragment of Earth. This finding could help us paint a better picture of the intense pounding early Earth got at the dawn of its life. It could go like this. Soon after the rock formed, an asteroid impact might have blasted it from Earth. At that time, our planet's satellite was 3 times closer to Earth than it is today. The collision was so powerful that this chunk of terrestrial rock found its way to the moon. Later, this fragment got engulfed in a lunar breccia, a motley kind of rock. Eventually, the rock was brought back home to Earth by Apollo 14 astronauts. Even though scientists had found meteorites coming from Mars and the moon before, it was the first time a rock from the moon turned out to be a terrestrial meteorite. They also found out that the rock had formed in a water-rich environment at temperatures and pressures corresponding to those at around 12 miles beneath the surface of our planet. In 2019, China's Chang'e 4 mission made history by landing on the far side of the moon. The mission's rover helped researchers visualize structures hidden deep below the surface of the satellite, revealing billions of years of lunar history. The Yutu-2 rover made this discovery with the help of its lunar penetrating radar. It imaged deep into the moon's surface and listened to echoes of sound bouncing back off structures hidden from view under the surface of the moon. It turned out Those structures were resting at depths of almost 1,000 feet. The research suggests that the first 130 feet under the surface are made up of layers of dust, soil, and rocks. The instruments also discovered a concealed crater that must have formed after a large object slammed into the moon's surface. Long, long ago, ancient lava was likely to be flowing deep underground. Researchers believe that the broken rocks around the formation might be debris produced by the impact. They also found that the volcanic rock layers were thinner the closer they were to the surface. Such a thickness variation of lava flows might mean a decrease in the number and magnitude of eruptions over time. So, lunar volcanic activity gradually dwindled since the moon's formation around 4.5 billion years ago. On the far side of the moon, there is one of the largest and oldest impact craters in our solar system, the South Pole-Aitken Basin. Unfortunately, from Earth, you can only see its outer rim, which looks like a huge chain of mountains. It's a ginormous 8-mile deep dent, stretching for more than 1,500 miles in diameter and covering 1/4 of the moon's surface. Astronomers are sure that this crater appeared when an asteroid collided with the moon around 4 billion years ago. And now, look at this gigantic chunk of metal the size of 4 states of Connecticut. As for its weight in pounds, it's enough to say that the number contains 18 zeros. This mysterious mass is hidden about 180 miles under the moon's surface, somewhere in the middle of the South Pole-Aitken Basin. It was discovered when GRAIL, which stands for NASA's Gravity Recovery and Interior Laboratory Mission, gathered data about our natural satellite. When examining this information, scientists noticed that in one place on the moon's surface, there was a weird change in gravity. After researching this phenomenon, they concluded that something mysterious was weighing down the basin floor there. So far, researchers haven't figured out the origin of the bizarre lump, but there are several theories. One of them claims that the finding is a chunk of dense oxide, which appeared when the moon was just taking its shape. At that time, the satellite was still covered with ancient oceans of magma, and the lump could be formed at the final stages of its cooling. However, most scientists support another theory, according to which the puzzling mass is part of the giant asteroid that once created the South Pole-Aitken Basin. Since the thing is metallic, it's probably the iron-nickel core of the asteroid. There might be a labyrinth of lava tubes on the moon. Not so long ago, astronomers received the results of underground topography and discovered a massive cave under the surface of Earth's satellite. It could be the result of the lunar volcanic activity that happened more than 3 billion years ago. Streams of lava hardened, creating a thick, hard crust on the outside. But inside, it kept flowing, melting the rock and creating tunnels and caves. Numerous small pits in the moon's surface discovered by NASA seem to be the openings to such lava tubes. If this theory is confirmed, the underground tunnels might serve not only as a convenient location for human-crewed space missions, but also as much-needed water sources for astronauts.
It's been decades since the last manned moon landing, Apollo 17, which happened in December 1972. Isn't it time we thought about going back to our dusty satellite, and maybe even staying there? NASA has made a promise on this subject. They're preparing to send astronauts on the moon again, perhaps by 2025. This will all happen through a program called Artemis. It's also going to include the first woman ever to experience the lunar surface. Now you might ask, why haven't we done this already? One former NASA administrator said something interesting on the subject. It's not because of scientific or technological issues. Problem was that the potential projects took too long and were just too costly. You see, space travel, especially when it involves humans, isn't easy on the pockets. It's true that, in recent years, NASA had budgets of billions of dollars. Sure sounds like enough money, right? Well, not when you check out their to-do list. That's because they have to consider everything. From telescopes and giant rocket projects to missions also targeting the Sun, Jupiter, Mars, and beyond. When you look at it this way, NASA needs to be very good at budgeting to achieve all those goals. It's not just because of finances, though. The moon itself is quite problematic. It poses real dangers that cannot be taken lightly. For starters, its surface is filled with craters and boulders that aren't easy to land on. Then, there is the moon dust, or regolith, if you'd like to call it by its scientific name. It was created over many years by meteorite impacts. It's extremely harsh and sticks to everything. It can potentially damage spacesuits, vehicles, and systems quite quickly. Also, dealing with the lunar habitat isn't a walk in the park either. The moon has no protective atmosphere. What this means is that for 14 days at a time, the lunar surface is faced with harsh rays from the sun. That period is followed by another 2 weeks of total darkness. All these changes create extreme temperatures, which us humans are not really accustomed to. There are solutions, don't worry. NASA is working on dust and sun-resistant spacesuits and vehicles. They're even developing a system that might supply electricity during those lunar nights. What's even more interesting about this system is it could come in handy on Mars too, once we get there. NASA also needs to draw in really smart people for its projects. Think about it. The average age of the people working for the mission control for Apollo 13 was just 26 years old. And these people had already been part of numerous missions by that time, which means they'd had considerable experience from a very young age. But here's where other individuals can help too. In recent years, it wasn't just NASA who's been working tirelessly to revolutionize space travel. There are many successful people out there with enough resources to join in on these efforts. Some are developing new types of rockets that can land on the moon too. In total, NASA landed 12 people on our satellite. It's definitely one of the most awesome moments in its history, if not the best. And those astronauts did amazing things up there. They brought back rocks, took snapshots, did science experiments, and even left flags behind. These were all important moments of the Apollo missions. But they weren't meant to create a safe place for humans on the moon. Scientists have had this idea of a lunar space station for a long time now. It's only logical. After all, it's just a 3-day trip from Earth. It means we can, technically, afford to make little mistakes here and there, without messing up the whole project. Plus, we'd learn so much before venturing even further into space. A moon base could provide fuel for deep space missions. We could also build telescopes up there and launch them way easier in space. It could also help us in another important project. Figure out how to make Mars habitable too. Not to mention, a lunar space station would help us learn more about the moon's origin. Who knows, it could even bring in some money because of all that fun, exciting lunar tourism. Either way, the Apollo moon program took a lot of work. For starters, let's look at the sheer number of people involved. Around 400,000, from every corner of the states. Not everything was picture perfect, tough. There were two main unfortunate events. Firstly, a fire mishap at the launch pad of Apollo 1. Secondly, an oxygen tank decided to throw a tantrum on Apollo 13, causing severe issues mid-mission. An important part of the project was Saturn V. It is to this day the most powerful rocket flown successfully, being 36 stories high. Still finding it hard to picture? This rocket stood twice as tall as Niagara Falls. Thanks to Saturn V, NASA successfully completed 13 missions. This included chauffeuring 24 astronauts towards the moon, with half of them even having a little walk on its surface. The existing rockets and space shuttles can't go beyond low Earth orbit. In simpler terms, they can't reach the moon with all the gadgets astronauts need to thrive. Current space vehicles are just not capable of carrying that load, at least not since the Apollo missions happened. Regardless, we did make a lot of progress on Earth and are ready to send astronauts to our satellite pretty soon. Here's where the Artemis project comes in. It's a program overseen by NASA. And to make sure it all goes well, NASA previously launched Orion, a spacecraft with no crew on board to orbit the moon and return to Earth. Think of it as an automated test drive. Before we actually send people out there again, we need to make sure all the devices work properly. One day, Orion will be the vehicle that will take astronauts to the moon again. It features a launch abort system to keep astronauts safe in case something bad happens during launch. It also has a service module, which is the powerhouse that fuels and propels Orion and keeps astronauts alive with water, oxygen, power, and temperature control. All these future projects make one wonder, what will life on the moon be like anyway? We can only use our imagination for now. Some say we'll be living in homes straight out of a fairy tale, something like a cozy hobbit hole. Living underground on the moon might be a must. That's due to the scorching temperatures and the lack of oxygen. If you add meteorite threats and the non-stop radiation, it's no wonder we can't just walk on its surface. What about transportation? Big and small companies alike are trying to create the ideal moon ride. If current estimations are current, one type of moon taxi will take off as soon as 2024. Unlike our current rockets, these space taxis won't have to deal with the harsh conditions of re-entering Earth's atmosphere. It will be easier for them to make multiple round trips. To support our lunar living, we'll need to have a special area for space taxis to safely take off and land. Think of it as a landing pad on a firm, flat stretch of moon surface, protected by walls to shield against moon dust. Moving around on the moon's surface will be made easier too. The next generation vehicles we're talking about will have their own controlled environment, which means you won't need a spacesuit while inside. Should feel like stepping out of your space ride for a bit. Then of course, you'll need to put on your spacesuit. All right. So we've got our homes and our rides sorted. But what about fuel? That's where the moon throws us a lifeline. The moon's lighter gravity means we don't need as much power to escape its pull. Plus, the moon has ice, and that's super handy. We might be able to convert this ice into rocket fuel. We'll need dedicated space gadgets to help gather this ice. One such tool is called Trident. It's like a drill, perfect for digging into the icy moon surface. Additional robotic helpers would then turn this ice into fuel and deliver it to a space gas station. If this works, rockets on their way to Mars could stop by for a quick fuel top-up before continuing their journey.
The moon has always been a source of wonder, myth, and mystery. It lights up our nights, controls the tides, and marks the rhythms of time. But what if the moon isn't what it seems? What if this familiar, glowing orb in the sky is not a natural object at all, but a hollow, perhaps even artificial construct? That's the central idea behind the hollow moon theory. A concept that blends science fiction with ancient lore, and dares to question everything we think we know about Earth's closest celestial neighbor. Let's explore the bizarre clues and strange stories that fuel this unsettling possibility. During the Apollo missions in the late 1960s and early 1970s, NASA astronauts left behind scientific instruments, including seismometers. In 1969, the Apollo 12 crew intentionally crashed a portion of their spacecraft onto the lunar surface. The result shocked mission control. The moon reverberated for over 50 minutes. Scientists said it rang like a bell. This was not a one-time event. Later impacts during Apollo 13 and 14 produced similar results. long-lasting, deep seismic vibrations that were unlike anything observed on Earth. Some theorists argue that this behavior could be a sign that the moon is hollow or has vast inner cavities. After all, nothing on Earth behaves that way unless it's mostly empty inside. NASA's explanation is more conservative. The moon has a dry, rigid crust with little water content, which allows seismic waves to travel much farther than they would through Earth's moist, fractured interior. Still, the Bell effect remains one of the strangest lunar anomalies on record. In many ancient cultures, there are legends of a time when there was no moon. Aristotle mentioned that the Pelasgians, the ancient people of Arcadia, lived before there was a moon in the heavens. The Zulu people of Africa tell stories of two brothers, Wawane and Mpanku, who brought the moon to Earth, an artificial object, hollow and controlled, which changed the weather and caused great floods. Ancient Sumerian texts also hint at a celestial object that arrived unexpectedly in the sky. These accounts span multiple continents and civilizations, alluding to a world that once turned without a moon. Are these myths simply poetic metaphors? Or could they be distant memories of real events passed down in the only language available to ancient humans, myth and story? The moon is the fifth largest natural satellite in the solar system, and by far the largest relative to the size of its planet. No other moon comes close in size ratio. This alone makes Earth's moon an outlier, but there's more. The moon is precisely the right distance from Earth, about 384,000 kilometers, to perfectly cover the sun during a total solar eclipse. The sun is 400 times larger than the moon, and also about 400 times farther away. This perfect 400 to 400 ratio creates an extraordinary visual phenomenon that allows scientists to study the sun's corona during eclipses. Coincidence? Maybe. But to some researchers, it feels more like design. And then there's the moon's orbit. It's almost perfectly circular, and it's tidally locked, meaning we always see the same face. We never see the far side of the moon from Earth, unless we send spacecraft around it. Why does this object behave so precisely? Is it a natural product of gravitational forces? Or something else? In 1970, Soviet scientists Mikhail Vasin and Alexander Sherbakov published a radical paper titled, "Is the Moon the Creation of Alien Intelligence?" They suggested that the moon may be a colossal, ancient spaceship, an alien construct disguised as a natural satellite. According to their hypothesis, the moon might have a metallic outer shell with an inner structure that once supported machinery, life, or monitoring equipment. They compared it to a planet-sized arc that could travel between star systems. While their paper was largely dismissed in the West, it planted the seed for countless other theories. Could the moon be a derelict alien spacecraft? Long abandoned, perhaps watching us still? More recent fringe thinkers have proposed even stranger ideas. Some argue that the moon might not just be a passive structure, but a kind of anchor for a simulated or controlled reality. In this vision, the moon is not just hollow, but alive with technology, possibly operating as a monitoring station, memory regulator, or even a civilization reset button. Ancient floods, magnetic pole shifts, and unexplained disasters. Some theorists claim these events correlate with specific lunar alignments or cycles. Others go further, suggesting that the moon is part of a larger system designed to keep human consciousness limited, trapped in cycles of forgetting and rediscovery. Is the moon helping to shape our very perception of time, reality, and evolution? It's impossible to prove, and perhaps that's the point. Even beyond the big theories, there are many small puzzles that don't quite fit. For example,
When scientists first studied moon rocks, they expected to find thick layers of accumulated dust, possibly several meters deep. Instead, the moon's surface dust was surprisingly shallow. Where did all the debris go? Radio signals sent to the moon sometimes bounce back with strange delays, suggesting interior reflections that aren't typical for solid rock. And then there are the mysterious transient lunar phenomena. Sudden flashes, glows, or color changes on the moon's surface. These have been observed by astronomers for centuries, yet remain unexplained. Mainstream science sees the moon as the product of a massive collision in Earth's early history, a fragment of the young planet that cooled into orbit. But for every answer science provides, there seem to be more questions. Why does this object behave so perfectly? Why do myths around the world speak of its arrival? And why does its presence feel so scripted? Whether you believe in the hollow moon theory or not, one thing is certain: the moon is far more than just a rock in the sky. It is a mirror to our imagination, a beacon to our ancestors, and maybe, just maybe, a puzzle we were never meant to solve. What if we built a huge tower on the moon? A tower that could provide future missions with light, power, and guidance technologies that could help astronauts explore our natural satellite. It's not something from a sci-fi book. It's a novel idea from Honeybee Robotics, one of the brightest space technology companies. The lunar utility navigation with advanced remote sensing and autonomous beaming for energy redistribution, or simply Lunar Saber, is a 328 tall pole. It's capable of holding 1 ton of equipment on top of it. But how could we build such a giant construction? No rocket would be able to hold and land such a giant pole on the moon. And building such a tower on the lunar surface without already existing infrastructure would be next to impossible. So, Honeybee might use the deployable interlocking actuated bands for linear operations Diablo system. It uses a rolled piece of metal and bends it into a deployable cylindrical structure that can support really heavy payloads. It would be easier to build it on the moon because gravity there is only 16% of that on Earth. The structure could serve as the base for Lunar Saber. Power is crucial on the moon, so putting solar panels along the sides of the pole would be super useful. The company is now discussing 2 types of solar panels. The first one is like a yo-yo extended from the top payload holder of the tower. It would envelop the metallic structure and allow access to the sun at all angles. The second option might involve the top part of the tower. It could deploy its booms to hold traditional solar panels and then track the sun. Power supply wouldn't be the only Lunar Saber's task. It would also be able to beam power to other devices, track other devices, and provide communication, light, and energy. Let's talk about these functions in more detail. If one mast of the pole was bathing in sunlight while another was lingering in shadow, the one with excess power would be able to beam power to the one lacking it. Plus, similar power beaming could happen between Lunar Saber and rovers and astronauts in spacesuits. To beam all that power effectively, though, the tower would need to know the precise location of those objects. That's where the second technology would come in. Lunar Saber could use a set of sensors to find and track other objects. Basically, anything in a direct line of sight could be tracked and powered by the tower itself. Lunar Saber could also act as a lunar cell phone tower. It would allow wireless communication in its network. And finally, it would be super helpful for astronauts to actually see where they would be going. Rovers wouldn't need to wait out the 2-week lunar darkness. Floodlights at the top of the tower could provide enough visible light for astronauts and rovers, which would allow them to effectively perform their activities at all times. But guess what? The tower could become even more useful. We could combine several towers in a mesh. It would allow astronauts to communicate more effectively. Plus, power could be beamed even from the other side of the moon. It would enable 2 main applications that have been a thorn in lunar exploration's side so far: constant communication with Earth and constant supply of solar power. The thing is, explorations on the other side of the moon are quite tricky. which limits the area of scientific research to the side directly facing Earth. But a strategically placed mesh of lunar sabers could allow communication back to Earth, and we would be able to explore the dark side of the moon. Since at least half of our natural satellite is always lit up, if we placed lunar sabers correctly around the surface of the moon, there would always be at least one bathing in sunlight. That one sunlit tower would then wirelessly transmit power to others in its line of sight. This process would keep going until power was beamed to the main astronaut's base, supplying them with power even in the cold lunar darkness. Unfortunately, at the moment, such technologies look unrealistic. We're not close to having wireless energy transmission over long distances. Even on Earth, we still need to use batteries and wires. It might be easier to launch many satellites into orbit around the moon than to create a network of giant communication towers.
There are a few theories about how the moon appeared in the sky, and recently a new idea has popped up. But before we discuss this newcomer, let's look at the most popular hypotheses of the moon's formation. The capture theory claims that Earth's natural satellite used to be a wandering body, something like a large asteroid. It had formed somewhere else in the solar system before it was captured by our planet's gravity when passing nearby. The accretion hypothesis suggests that the moon formed in orbit around Earth at the same time as our planet appeared in the darkness of the cosmos. Then, there's the fission theory that says that at one point in its development, Earth was spinning so fast that some of its material broke away and started to orbit the planet. And the giant impact theory, which is the most popular these days, claims that the moon formed during a collision between Earth and another hypothetical planet called Theia, which was way smaller, probably the size of Mars. The resulting debris collected in an orbit around Earth and formed the moon. And now, let's move to the new theory you've been patiently waiting for. According to it, our satellite might have formed immediately, in a matter of hours, after the collision between Earth and Theia. The material from the two planets was likely launched directly into Earth's orbit right after the impact. It formed the moon and left traces deep inside Earth. In previous scenarios, Theia's remains were thought to have been scattered all over space, mixing with just a bit of the material coming from our own planet. But then, why do we see such shocking similarities between the moon's and Earth's compositions? Could it be that Theia was isotonically and chemically similar to Earth? Unlikely. But according to the new theory, more material from Earth was used to create the moon, its outer layers in particular. It might explain this similarity in composition. One more theory also tries to explain this mysterious similarity, the synestia model. According to it, our satellite formed inside a swirl of vaporized rock left by the collision. But this theory can't explain the moon's current orbit. The new single-stage theory does offer us plausible explanations for both the similarities in composition and the orbit of the moon. It might also provide us with some answers to previously unsolved mysteries. Since this scenario puts the moon into a wider orbit and gives it an interior that is not fully molten, it can explain the satellite's tilted orbit and thin crust. In any case, to confirm one of these theories, we need to analyze future lunar samples that will be brought to Earth by NASA's upcoming Artemis missions. Scientists will be able to get their hands on some material from deeper beneath the moon's surface and compare if real data matches these simulated scenarios. In the past, the Apollo missions already brought back about 1/3 of a ton of rock and soil from our satellite. These samples showed that Earth and the moon had some remarkable chemical similarities. They could only suggest one thing. These space objects had a linked history. If the moon had formed elsewhere and been captured by our planet's gravity later on, its composition would be very different from that of Earth. But if the moon had been created at the same time as Earth, or if it had broken off our planet, the type and proportion of minerals on the moon would be the same as on Earth. But they are a bit different. The moon's minerals contain less water than their terrestrial counterparts. The satellite is also richer in materials that form rapidly at high temperatures. That's why the most accepted model of the moon's formation these days is the giant impact model. Meteorites coming from the moon are a great source of data for studying the origins of our satellite, too. They can tell us even more about the moon than Apollo samples, all because such meteorites come from all over the surface of the moon. Meanwhile, Apollo samples were collected just in one place near the equator, on the near side of the moon. On a starry night, you look at the sky and see twin moons high above Earth. It's a view science fiction fans can only hope for, but it could have been a reality billions of years ago. If we want to be super precise, 4 billion years ago. A recent model suggests that the highlands of the moon's far side could have been created by a collision with a smaller companion moon in an event dubbed the Big Splat. The mystery of why the near and far sides of the moon are so different have been puzzling astronomers for decades. The near side of our natural satellite is low and flat, while the landscapes of the far side are high and mountainous. That part also has a much thicker crust. It leaves us with a somewhat lopsided moon. According to the giant impact model of the origin of our satellite, a Mars-sized object crashed into young Earth early in the history of the solar system. This event produced loads of debris that then coalesced and formed the moon. The new model, though, suggests that there could be a second moon orbiting around Earth. It would have been around 750 miles in diameter and could have formed in the same collision. Later on, this smaller moon could have fallen onto the bigger one, coating one of its sides with an extra layer of solid crust tens of miles thick. This model fits the moon-forming giant impact theory surprisingly well. After all, it does predict that there had to be tons of debris left in orbit around Earth after the collision, besides the moon itself. It also agrees with what we know about the dynamical stability of such a system, the ages of lunar rocks, and the timing of the cooling of the moon. There are other computer models that suggest a companion moon too. Another team of scientists used computer simulations to figure out the dynamics of the collision between the moon and a potential smaller companion. According to their model, it was about 1/30th the mass of the main moon. They tracked the distribution of lunar material in the aftermath of this event and its evolution. They found out that the impact would have been relatively slow, at a mere 5,000 miles per hour, which is slow enough for rocks not to melt. Plus, no impact crater would have formed at such a speed. Instead, the crust and rocks from the smaller moon would have spread over and around the bigger moon. On the other hand, such a collision sounds a bit weird. Being slow, it doesn't leave an impact crater. But at the same time, it splats material onto one side of the bigger object. There is a theory that the companion moon was originally trapped at gravitationally stable Trojan points, sharing the moon's orbit. But later, it became destabilized after the moon's orbit moved further away from Earth. The collisions could have happened anywhere on the moon, but that might be the reason why today's moon is lopsided. This model also explains the differences in the composition of the moon's crust. On the near side, it contains more potassium, rare earth elements, and phosphorus. These elements are thought to have been concentrated in the magma ocean that remained under the solidified crust of the moon. In the simulations, the collision squished this layer onto the near side of the moon. But even though this model explains a lot of things and answers loads of questions, the theory remains unconfirmed. We still don't know the full history of the moon and what really happened there. Scientists say that the best way to figure it out is to get more data from lunar orbiting spacecraft. An even better way to get information would be a human mission to study the moon. In the universe, wonders are never in short supply, and each one tells us a story about time, space, and our place among the stars. One such tale revolves around our closest celestial neighbor, the moon. This enigmatic satellite, accompanying Earth for billions of years, has captivated human attention throughout the ages. From the first shamans worshipping the moon to modern-day scientists probing its surface, it remains a key to understanding our past, present, and perhaps future. Here's the Sun. It's in the center of our solar system. Mercury, Venus, and here's Earth and the Moon. The Earth takes 365 days to orbit around the star. At the same time, the Moon revolves around the Earth and completely orbits our planet in 27 days. The Earth creates a shadow zone, and sometimes the Moon passes through it. The shadow is cone-shaped and gradually narrows. The Moon is 238,000 miles away. That's like 9 lengths of the equator. At this distance, the width of the shadow is about 2.6 times the width of the Moon. When the Moon is in this zone, direct sunlight doesn't reach it. That is, it should have disappeared, but instead it becomes red. All because the sun's rays pass through the Earth's atmosphere. They scatter and most of the blue light disappears. But the red and orange rays continue and hit the surface of the Moon. Voila! You see a phenomenon called the blood moon. By the way, this curvature of light occurs at sunsets and dawns. The atmosphere scatters the blue light, and you see a red and orange sky. If you were standing on the surface of the Moon during a total lunar eclipse, planet Earth would be exactly between you and the Sun. So you would be able to observe the solar eclipse. The surface of the Earth would become entirely dark for you. All you'd see would be the Sun's corona illuminating the edges of the planet. The Earth from the surface of the Moon is almost the same size as the Moon from the surface of the Earth. Such a red eclipse of the Moon is rare because several factors must coincide. One of them is that the Moon must be full. Usually, you can see 2 total lunar eclipses a year. In 2038, you'll be able to see 4 such eclipses, and the eclipse itself can last up to 108 minutes. But this is rare, and the last time such a long blood moon was seen was in 2000. Many years ago, people didn't know so many facts about our satellite, and the sight of a red moon frightened them. It was a bad sign and a harbinger of trouble. People who knew the schedule of eclipses could take advantage of it. For example, Christopher Columbus had an astronomical almanac and knew when the next lunar eclipse would occur. He frightened the inhabitants of the Caribbean islands when he predicted the red moon. The moon is gravitationally locked with the Earth. That's why it is always turned to us with one side, like Mercury and the Sun. But the moon doesn't stand still. It's gradually moving away from our planet. About 1.5 in a year. Not quickly, but in about 600 million years, it will have shrunk in our sky so much that we won't be able to see lunar eclipses anymore. Do you see this crater? It's Tycho. It's visible during a full moon because of these bright rays that extend thousands of miles from its epicenter. This is the youngest crater on the moon. Scientists say it appeared there due to a meteorite impact about 109 million years ago. At that time, dinosaurs were roaming the surface of our planet, and they may have seen the impact. It was most likely accompanied by a big explosion and looked like a salute in the night sky. In wrapping up, our relationship with the moon is a testament to the beauty and mystery of our universe. Its patterns, movements, and influence on Earth serve as a reminder of the grand cosmic dance we're a part of. If you're intrigued by such celestial wonders, do consider subscribing for more insights into our incredible universe.
Recently, the James Webb Space Telescope has spotted something no one expected to see. It might be a new kind of star that was born in the early universe. And the most shocking thing about this star is that it's likely to be powered by dark matter. The thing is, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. These days, we have several detectors looking for weakly interacting massive particles. That's what dark matter might be composed of. But so far, researchers have found nothing of the kind. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Now, returning to dark stars that might be powered by this mysterious dark matter. The very concept of such stars still remains hypothetical. Astronomers aren't sure that the images received by James Webb show exactly them. But even if one of the three candidates spotted by scientists turns out to be this new kind of star, it could offer us a glimpse of how stars formed in the early universe. Plus, we would probably be able to find out something new about dark matter and even explain how supermassive black holes appeared out there. The first time someone mentioned the term dark star was in 2007. These space objects could have been some of the first types of stars to form in the universe. They haven't been observed yet, but astronomers think they might be powered by heat that is generated during dark matter interactions rather than by nuclear fusion reactions, like it happens with our sun. Experts believe dark stars would probably look extremely weird. They could have appeared from clouds of hydrogen and helium that drew in excess dark matter. We still don't know the nature of dark matter. But there's a theory that particles of dark matter might be able to interact with themselves, annihilating one another during collisions, and, thus, producing huge amounts of light and heat. Then, this heat could have prevented the cloud of hydrogen and helium from condensing. It means these gases wouldn't have been able to create dense, hot cores similar to those the stars existing today have. And if this gas cloud wouldn't have condensed, dark stars could have grown to truly enormous size. In theory, a dark star could be around 10 times as wide as our planet's orbit around the sun. Imagine the sheer size of such a space monster. These stars would also be millions of times as massive as our star, and their light could be billions of times brighter. It might be the reason why James Webb managed to spot them. To check for dark stars that might be lurking out there, scientists thoroughly examined the images from a JWST survey of early galaxies. They spotted more than 700 objects that could have appeared in the first 100 million years after the universe appeared. That's exactly the time when dark stars were probably born. Light from objects that appeared so unimaginably long ago is stretched, or, as astronomers call it, redshifted. So, the team examining the images picked 4 objects that had already been confirmed to be extremely redshifted. It meant that the researchers were looking at some of the oldest space objects observed so far. These objects might be tiny galaxies from the times when our universe was just a baby. Unfortunately, since they're so far away, the resolution of James Webb isn't enough to figure out whether they're indeed galaxies or just large super bright stars.
What if dark matter doesn't exist? And what if the universe is way older than we thought? Like 27 billion years old instead of a mere 13.8. It sounds insane, but that's what one scientist is saying. But first off, you know how the universe is mostly made up of stuff we can't see. We do have normal matter like planets, stars, and whatnot. And then there's dark matter and dark energy. They are supposed to make up most of the universe. Well, Rajendra Gupta, a physics professor from the University of Ottawa, is saying, folks, maybe we don't really need dark matter or dark energy to explain the universe. Let's have a look at his theory. So, Gupta has been mixing up 2 big ideas. One is called tired light, and the other is called CCC, which stands for covariant coupling constants. But we'll just call it CCC from now on. Normally we think that things like the speed of light or the charge of an electron are set in stone. But what if these so-called constants actually change over time? That's the CCC part of Gupta's theory. Then there's the tired light thing. When we look at distant galaxies, the light we see is stretched out and redshifted. Most people explain that by saying that the universe is expanding. But Gupta's idea is, what if light just gets tired as it travels long distances and simply loses energy? These 2 ideas can potentially explain how the universe works, and you don't need dark matter or dark energy to fill in the gaps. But why do people even believe in dark matter altogether? A quick backstory. Back in the 1930s, astronomer Fritz Zwicky noticed that galaxies were moving in weird ways that didn't match up with what we could see. So he thought there must be some invisible stuff out there pulling on everything, what we now call dark matter. And since then, scientists have found more clues confirming this theory. Like the fact that galaxies spin way faster than they should if we were just counting visible matter. So most scientists think dark matter is like this invisible glue holding galaxies together, making up about 27% of the universe. Well, Gupta disagrees. He also claims that the universe is actually almost twice as old as we think. According to him, the expansion of the universe isn't driven by dark energy either. It's just that the forces of nature are getting weaker over time. He also focuses a lot on redshift, the way light stretches and gets redder as it travels through space. The scientist believes that when we look at the way galaxies are spread out and compare stuff in the old universe to what we see now, the data actually works without needing dark matter to explain it. If Gupta's theory was correct, it would flip everything we know on its head. It could even explain things like how galaxies formed and what the Big Bang really was. We could even figure out more about that leftover glow from the early universe, the cosmic microwave background radiation. But unfortunately, his idea is kinda outdated. Most scientists are sure there's a lot of evidence for dark matter and dark energy, so Gupta would need to find some really solid proof to convince people. Plus, scientists are working on different theories these days. They're measuring cosmic radiation, examining distant stars, and digging through tons of data to see which theory might be correct. More and more powerful telescopes pop up all the time. So we might actually get some answers pretty soon, and most likely they won't involve tired light.
One of the greatest riddles the universe baffles us with is why there is so much more matter than antimatter. The thing is, according to the laws of physics, you can create and destroy matter and antimatter only in equal amounts. But when we look at stars, galaxies, and other large-scale space objects, we see that all of them are made of matter. Only small traces of antimatter can be detected in the cosmos. So the question is, could an equal volume of antimatter exist somewhere? Maybe at one point it just got separated from regular matter? And if it's so, could black holes be that place that contains all the lost antimatter in the universe? If the total mass of supermassive black holes was approximately the same as the amount of that missing antimatter, it could really be the answer. So let's try to figure it out together. At first sight, it may seem that the universe isn't homogeneous and galaxies clump and group together. But if you look at it on a very large scale, you'll understand that the universe has the same properties everywhere. If there was a galaxy made out of antimatter instead of regular matter, we would spot a great number of matter-antimatter annihilation signatures. But since we don't see them anywhere, not in clusters of galaxies, not in individual ones, and not even in colliding clusters of galaxies, we can conclude that almost 100% of the universe is matter. But this is kind of confusing because, according to the current laws of physics, there are no mechanisms that can create more matter than antimatter. Let's take quarks, elementary particles that are building blocks of all visible matter in the universe. Every time we create a quark, an antiquark also forms. And when a quark is destroyed, an antiquark stops existing too. The only way to create more or less matter is to make equally more or less antimatter. The only seemingly logical explanation can be that in the universe's past, more matter than antimatter was created. In the standard Big Bang picture, when the universe was in its early stages, particle-antiparticle pairs of all known and yet to be discovered particles appeared in tremendous abundance. All because at high temperatures and densities, new particles-antiparticles can be produced spontaneously from pure energy. Then these pairs annihilate, producing pure energy photons again. When the universe cools down, it runs out of energy to create new pairs, and the annihilation process becomes prevailing. But what if, at one point in the early universe, something made antimatter collapse into black holes while leaving regular matter behind? After all, we have discovered quite a few ancient supermassive black holes. But then, there's a theory of direct collapse. According to it, some black holes don't need stars to run out of their space fuel and go supernova. Instead, they simply collapse. This process could create seeds, large and fast enough to grow into the young quasars we see today. According to some theories, quasars contain massive black holes. So we can most likely rule out supermassive black holes. But there are also hypothetical primordial black holes. They're often viewed as candidates for dark matter. These holes, if they exist, can't be too light, otherwise they'd have decayed. Neither can they be too heavy. This way, we'd have already spotted them. So, most of the possible mass ranges allowing for primordial black holes to be the missing antimatter are already ruled out or very tightly constrained. But in any case, astronomers have managed to estimate the total mass of all black holes in the universe, and it turns out to be approximately 0.007% of the total energy in the universe. And given that there's around 700 times as much normal matter as there are black holes, we can make a disappointing conclusion. Black holes can't be where antimatter is hiding. Neither can antimatter form black holes. The universe somehow managed to make more matter than antimatter at some point in the past. That's actually why we appeared in the first place. But how exactly it happened still remains one of the biggest mysteries in physics today. Can a planet be bigger than its parent star? Well, if you mean a star like our sun, it's highly unlikely. But what if it was a white dwarf, the remnant of a star similar to ours that went out after shedding its outer layers and leaving behind nothing but the core? This core is what we call a white dwarf. Usually, it's around the size of our home planet. If a star had a planet bigger than Earth before it extinguished, it's possible that such a planet could survive all the chaos. In this case, a planet that is bigger than its star might actually exist. And we've even found planetary systems like this. But there's one problem. A white dwarf isn't a real star like our sun anymore. It doesn't produce energy, just sits out there getting cooler and cooler. So probably such systems don't count. For comparison, the sun is working non-stop. It is fusing hydrogen into helium in its core. It has been doing it for more than 4 billion years and is going to keep doing it for the next 7 or 8 billion years. The sun is 10 times as wide as the largest planet in our solar system, gas giant Jupiter. And sadly, you can't get a planet much larger than that. If you start adding mass to such a world, it will get smaller, not bigger. So it seems you can find a planet larger than the sun. But there are also dim red dwarf stars. They're the smallest out there, barely massive enough to maintain fusion in their cores. The tiniest stars that we know about have been discovered recently. If astronomers' conclusions are correct, then both of them can hardly fuse hydrogen into helium. And it takes about 0.077 times the sun's mass, or 75 masses of Jupiter, to be able to do that. And still, they're real stars, just very tiny, smaller than Jupiter. One of them is only about the size of Saturn, which must mean that stars can have planets bigger than they are, right? Well, theoretically. When it comes to practice, you can hardly find such planetary systems. We've found and observed quite a lot of exoplanets, which are worlds orbiting other stars. It seems that there are indeed loads of trends out there in space, different masses, sizes, brightness, and so on. But the main trend? Red dwarfs don't usually have gas giants orbiting them. If they do have planets, those are typically small, rocky worlds, more like Earth. Those are also called terrestrial planets. For example, a red dwarf called TRAPPIST-1 has 7 Earth-sized planets orbiting it. But gas giants circling around red dwarfs are extremely rare. Hardly 1 in 100 tiny stars can boast such a planet. This number can be even smaller since the research has been done using candidate planets which haven't been confirmed yet. Plus, the smallest stars are also the dimmest. It means they are extremely hard to detect, and it's incredibly hard to figure out whether they have planets orbiting them, and if they do, whether these planets are gas giants or terrestrial worlds. Still, it's possible that a system where the planet is larger than its parent star exists. But the probability is statistically very low. At the same time, red dwarf stars are very numerous. They're actually the most common kind of star in the galaxy, making up around 70% of all stars. And even though really tiny red dwarfs are relatively rare, there still must be millions or probably even billions of them in the galaxy. And if there's even a small fraction of red dwarfs with gas giants orbiting them, it might still mean that a lot of such systems exist in total, and some of them can have planets bigger than their host star.
What would it be like to live on a planet traveling around a star so huge that, in comparison to it, our sun looks like a tiny speck of dust? Well, you could find it out if you manage to visit a planet orbiting WOH G64. It's a red supergiant, an enormous star dwelling in the Large Magellanic Cloud, which is a satellite galaxy located not too far away from our home Milky Way galaxy. Red supergiants in the Large and Small Magellanic Clouds provide an excellent opportunity to observationally test the current stellar evolution theory for massive stars. WOH G64 is likely the largest star we have found so far. It's a real heavyweight emitting an incredibly bright light. To understand the sheer size of this mega star better, let's put it into perspective. Compared to our star, the radius of WOH G64 is around 1,540 times bigger. In other words, it's like comparing a tiny grain of sand to a basketball. If we placed WOH G64 at the center of the solar system, the surface of this star would extend past the orbit of Jupiter, swallowing up Mercury, Venus, Earth, Mars, and Jupiter itself. You see, the average radius of Jupiter's orbit is around 1,000 times the radius of the Sun. As for Saturn, the radius of its orbit is around 2,000 times the radius of the Sun. That's why WOH G64, with its average radius being 1,500 times the radius of the Sun, fits right in between. Oh, and if you spread out the star's dust envelope, it would cover a distance of about 1 light year, or 5.88 trillion miles. The star is not only ginormous, but also immensely bright. In fact, it's one of the most luminous stars we know of. Luminosity is the total amount of energy a star emits per unit of time. And the light coming from WOH G64 is around 282,000 times brighter than the light from our Sun. But perhaps one of the most amazing features of WOH G64 is the dust envelope surrounding it. In 2007, astronomers, with the help of the Very Large Telescope, discovered that WOH G64 was surrounded by a torus-shaped cloud. It's so thick that to some extent it obscures the star. The dust envelope is made up of the material the star has expelled, and it contains between 3 to 9 times the mass of the Sun. The star we're talking about was discovered in the 1970s by Bengt Westerlund, Olander, and Hayden. That's where the WOH in the name of the star comes from. It's an abbreviation made up of the first letters of the discoverers' names. By the way, Westerlund also discovered another remarkable red supergiant, Westerlund 126. It was spotted in a massive star cluster called Westerlund 1 in the constellation of Ara. But back to WOH G64. Scientists have noted that this star lies very close to or even beyond the Hayashi limit. It is a theoretical constraint upon the maximum radius of a star for a given mass, a condition where the inward force of gravity is matched by the outward pressure of the gas. By now, the star WOH G64 has reached such an evolved state that it can no longer hold onto its atmosphere because of super low density, high radiation pressure, and relatively opaque products of thermonuclear fusion. That's why its average mass loss is among the highest known to us so far. It's unusually high even for a red supergiant. WOH G64 also shows an unexpected spectrum of nebular emissions. The hot gas is rich in nitrogen and has a radial velocity more positive than that of the star, which is quite an unusual phenomenon. The star might have a potential companion, an O-type main sequence star. If it turns out to be true, then WOH G64 will be classified as a binary star. At the same time, so far, there have been no confirmations of this theory, partly because the intervening dust clouds make the examination of the star very difficult. In any case, WOH G64 is absolutely fascinating, not only because of its huge size, but also because of its unbelievable luminosity and mysterious dust envelope. It's a great example of how unexpected and amazing our universe can get. Besides, such outstanding large stars are undoubtedly an important astronomical observation. The results of studies of such objects correct the restrictions on the properties of stars within the framework of modern models. For testing the applicability of models, the exceptions to the rules are most valuable.
Scientists have found an invisible star at the Milky Way center, a star that helped our galaxy be born. 26,000 light-years away, in the galactic center, a massive, invisible object started spreading everywhere, and you don't even know that you're breathing it right now. It all started in the 70s, when an astronomer named Vera Rubin was studying the Andromeda Galaxy. She decided to check whether stars move in a predictable way. Now let's say you're spinning a ball on a string around yourself. The closer the ball is to you, the faster it moves in a tight circle. But if you let the string out longer, the ball moves more slowly in a bigger loop. That's how gravity works. And the same goes for planets. The closer ones, like Mercury, zoom around quickly, completing their orbits in months. The far ones, like Neptune and Saturn, take their time, decades, to make one rotation. The stars themselves should orbit the centers of their galaxies the same way. The closer ones move fast, the farther ones are slower, right? But when Vera measured the speeds, she saw something impossible. They weren't slowing down. The faraway stars were moving just as fast as the ones near the center. By all logic, the galaxies should have torn themselves apart, but they didn't. And that meant something was holding them together, something undetectable, some massive invisible object in the galactic center warping reality without ever revealing itself. So she checked over and over with different galaxies. This wasn't a fluke, it was happening everywhere. Rubin had accidentally uncovered proof that galaxies were drowning in something far heavier than all the stars, planets, and gas in our entire universe combined. It was holding us with ghostly hands. Astronomers called it dark matter because it doesn't glow, doesn't reflect light, doesn't seem to interact with anything at all. It's just there. But all the calculations show us that it exists, and not merely exists, but makes up 85% of all the mass in the universe. We know that it sculpted galaxies. Without it, the world as we know it wouldn't exist. And yet, just like with an invisible star scientists found at the Milky Way center, the only way to detect it was through gravity. So how do you find something that refuses to be found? Recently, scientists discovered there might be an invisible star at the Milky Way's center, and this fascinating discovery might finally help us understand what dark matter looks like. They began looking for dark matter's fingerprints, any signs of its presence anywhere. They studied how galaxies moved and smashed particles together in giant machines, hoping to create tiny bits of dark matter in the lab. This didn't really lead to anything. They didn't even know what to look for. Is dark matter even made of particles? There was a theory that suggested that it's made of ghostly particles that barely touch anything, or even weirder ones that might flicker in and out of existence in the blink of an eye. There was a problem, though. If dark matter really worked like that, then the centers of galaxies should be packed tight. Tons of matter would be crammed into a tiny space. But in our universe, galactic cores seem strangely soft, spread out, almost gentle. A new theory emerged, and it was wild. What if the dark matter at the heart of galaxies isn't made of heavy particles at all? What if it's made of something so delicate that it behaves more like a strand of hair? These hairs could be made of something incredibly light, lighter than anything we've ever seen, and billions of times smaller than a neutrino, which is already the lightest known particle. They called this idea fuzzy dark matter, and it might change everything we thought we knew about the universe. A team of astrophysicists wanted to test this idea, so they ran a simulation, creating a simple model of a galaxy with two main ingredients: a whole lot of fuzzy dark matter and a little bit of gas, the same kind of gas that forms the stars we can see. They pressed start and just let the system evolve by itself, watching how the two would interact. At first, everything was pure chaos, but then the fuzzy dark matter started to gather. It pulled itself together, forming a massive invisible object near a galactic center. The gas followed, spreading throughout this ghostly mass, mixing with it and glowing faintly. And then, it suddenly formed something incredible: dark stars. Not typical stars like our sun, blazing with heat and light. Instead, It's enormous, massive, invisible objects, a hybrid of two different kinds of matter. We've never seen anything like this before. An object that would stretch across thousands of light years, and yet they'd be almost weightless, more like cosmic puffy clouds than anything else. Scientists called them Fermion boson stars. Finally, this dark matter thing is starting to make sense. The core of this strange invisible star would have just the right density, not too dense, not too loose, and it looked exactly like what astronomers actually see in real galaxies. If it's confirmed, then it would finally explain how dark matter behaves and works. And if they're right, then every galaxy in the universe could be tied to one of those vast unseen giants. The Milky Way hidden star might be one of them, shaping our galaxy in ways we never realized. What's wild is that this stuff wouldn't behave like normal matter. It wouldn't form anything solid. Instead, it would be more like a complex, ever-moving web of filaments or hairs. This also means that Earth might be completely surrounded by it. Dark matter still follows the rules of gravity. As it moves past planets and stars, gravity pulls it into focused streams, so it's both hugging and passing through our planet, wobbling consistently. If we could see them, they might look like glowing invisible threads everywhere, and they'd pierce right through the planet, stretching far into space. But this is only the beginning. Now scientists need to refine their models, make them even more detailed, and compare their predictions to real galaxies. But this dark star discovery in the galaxy's center isn't our only clue. Luckily, the universe has given us a way to look for that fingerprint: gravitational lensing. When light from a faraway galaxy travels toward us, it sometimes passes by another massive galaxy on the way, or other massive objects with crazy gravity. Instead of continuing in a straight stream, light actually gets bent around the massive object because of that gravity. And when it finally reaches us, it creates a distorted and magnified version of the original galaxy. Basically, it's like looking through a piece of curved glass. If dark matter is fuzzy, then it should leave a strange pattern on these distorted images. Things should be a bit wavy and unclear. Scientists needed the perfect object to study this, and they found one. A faraway galaxy whose light was bent by gravity, creating a strange stretched-out image. They used super-powerful radio telescopes, connected them all over the world, and turned them into one giant telescope as big as the Earth itself. With this, they could zoom in so much that they could see details of that galaxy as tiny as a grain of sand on the moon. Then they ran a huge experiment. They created their own fake versions of this picture, simulations with various sizes of fuzzy dark matter particles. And at a certain point, they found the perfect match. This helped us calculate the exact mass of dark matter particles before we even detected them. And the clues are leading us right to our own galaxy. It seems like densest parts of these hairs, the roots, might be super close in the cosmic scale, just tens of thousands of miles from Earth. That's close enough for a space probe to reach. Now that scientists have found this invisible star at the Milky Way center, we just need to study it up close, send a mission to one of these roots, and then we might finally crack the greatest space mystery of all.
Imagine a universe made of antimatter. In this alternate reality, the building blocks of matter are made up of particles with opposite charges, creating a strange and wondrous world. What would it look like? Would the laws of physics be inverted? Would time run backwards? Buckle up and let's find out. First off, let's figure out what antimatter is. We know that our universe is composed of matter. Matter is made up of tiny particles called atoms. These atoms are made up of protons, neutrons, and electrons, which together form matter and make up everything around us and what we're all made of. Antimatter, on the other hand, is just like regular matter, but the opposite. Just like how superheroes have opposite powers from their villains, antimatter has opposite properties from regular matter. So, while regular matter has protons with positive charges, antimatter has antiprotons with negative charges. Instead of electrons, we have positrons, And instead of neutrinos, we have antineutrinos. It's like the mirror image of everything we're familiar with. Now, here's an interesting part. When an antimatter particle and a matter particle collide, they annihilate each other and release a huge amount of energy. This is both a benefit and a drawback. On one hand, because of this property, studying antimatter is very difficult and expensive. We have to be very careful to ensure that antiparticles don't come into contact with ordinary atoms and don't annihilate each other. On the other hand, the huge amount of energy they release could revolutionize our lives. Perhaps one day, we'll start using them in propulsion systems for space travel. Imagine how amazing that would be! Scientists suggest that at the beginning of the creation of our universe, immediately after the Big Bang, matter and antimatter were equal. But this raises the question, where did the antimatter go? If they were truly equal, our universe would have been instantly destroyed before it could have been formed. Particles and antiparticles would have annihilated each other. Unfortunately, scientists themselves are not sure. They have a theory that the laws of physics were slightly different in the early universe, leading to an imbalance between matter and antimatter. So, after the Big Bang, particles and antiparticles began to mutually annihilate each other. However, for some reason, antimatter started to disappear. In the end, matter won. This process led to the creation of our universe. In the science world, it's known as baryogenesis. However, there are also scientists who offer more grandiose ideas. For example, a team of Canadian scientists from the Perimeter Institute for Theoretical Physics, led by Neil Turok, have proposed their own theory. They suggest that two universes were born at the moment of the Big Bang, our universe and a parallel one, consisting of antimatter. This is where all the antimatter has gone. According to this theory, at the time of the Big Bang, two universes were born, and then they separated. As the distance between these universes grew, the interaction between particles and antiparticles became weaker and weaker, until matter won in our universe and antimatter in the other. But the most important question is, what would this mysterious universe made up of antimatter look like? You may imagine a universe where everything is flipped. The stars shine with an eerie blue light instead of yellow. Buildings are made of glass that reflects light in the opposite direction, and laws of physics work in the opposite way. After all, antimatter has the opposite charge of normal matter, so isn't that logical? However, it's not that simple. Initially, scientists believed that this universe could be identical to ours in everything, all due to a property that used to be known as CP symmetry. The C stands for charged symmetry and means that each elementary particle has a twin with an opposite charge. The P stands for parity symmetry, meaning the symmetry of space. That is, all three directions in our world have opposite directions in the alternate universe. This basically means something like laws of physics are the same no matter what the location is and what type of particle is being considered. So, if you were to run the laws of physics in reverse, or in a different location, or with different particles, the results should be the same. In simple words, scientists initially assumed that the universe of antimatter would be a mirror image of ours. It would be a pretty boring world where everything would be exactly the same as here. But in the 1950s, scientists were mind-blown by an unexpected discovery. Neither of these symmetries held true. For example, if you take a piece of cobalt-60, it will emit particles that spin in one direction. But if you take the opposite of cobalt-60, the particles it emits will spin in the opposite direction. But they were expected to spin in the same direction. So what's going on here? Basically, it turned out that CP symmetry didn't work for certain weak nuclear reactions. The weak nuclear force is just weird like that, I suppose. This observation puzzled scientists for years, and then they finally figured out how to solve this mystery. They added another letter to CP symmetry, T, which stands for time reversal symmetry. This means that the antimatter universe, time must flow from the future to the past. In this case, the CPT property held true, so it turns out that the antimatter universe would be a mirror image of our universe, but with time flowing in the opposite direction. So there may be a version of you in this antiverse, watching this video on your upside-down computer, already knowing the ending. Isn't that crazy? So, although this universe would look similar to ours, it would also be fundamentally different. In this world, things would unravel instead of coming together. For example, broken objects would come back together to form whole objects. People would age in reverse, like Benjamin Button, and apples would fly up from Newton's head back to the tree. This, of course, is all purely hypothetical. It's very difficult for us to imagine a world where time flows backwards. We can only imagine how surreal this inverted reality would look like. But this is what the data suggests for now. There might be something we don't know yet that would make the antimatter world different. But as far as we know today, it seems this is what a mirror world made of antimatter would look like. Scientists are still studying antimatter and its properties. Understanding these properties is important for a number of reasons. First of all, it gives us a better understanding of the universe and its origins. The imbalance between matter and antimatter in our world is one of the biggest mysteries in physics. Studying antimatter can help us understand why this is the case. Second, it would give us a better understanding of particle physics and subatomic particles. This knowledge can help us unlock the secrets of the universe and make new discoveries in physics. And, of course, let's not forget about all the possible technological advancements. Antimatter has the potential to be used as a source of fuel for future space missions and other technologies. We could use this in propulsion systems to travel from planet to planet. We could also use antimatter in medicine, for example, for cancer treatment. Also in medical imaging, antimatter particles can be used to produce high-resolution images of the inside of the body, giving doctors a better view of what's going on. So, in other words, understanding the properties of antimatter is very important for science. It's a fascinating field of study that has the potential to unlock some of the biggest secrets in the universe. A universe made of antimatter would be a fascinating place. It would be very interesting to visit there and see how everything works. And the true nature of an antimatter universe remains a mystery, waiting to be explored and understood. But let's hope that we'll figure these mysteries out in the future.
Now in space, inky darkness between blinding points of light does a great job. It hides black holes, gaping, hungry, and scary. Their blackness makes it really difficult for astronomers to find detailed information about these space monsters. When a powerful and massive star reaches the end of its life, it can't just fade into nothingness. One of the most likely scenarios, the star will run out of its nuclear fuel. Then, in a blazing flash of light, it'll collapse under its own gravity. If the star was large enough, it'll turn into a black hole. There's a hypothetical type of black hole called primordial. Scientists have never gotten any real proof of their existence. These holes are insanely old and quite tiny, by black hole standards, that is. Astronomers believe they could appear several milliseconds after the Big Bang. At that time, stars and galaxies weren't born yet. It means primordial black holes probably witnessed the entire history of the universe. By now, the smallest primordial black holes have most likely evaporated away, but the bigger ones can still be scattered out there in space. But how did primordial black holes appear in the first place? In the very beginning, space wasn't the same. In some regions, it was hotter, in others, cooler, and some areas were extremely dense. Scientists believe these dense spots could collapse into primordial black holes. The most curious thing, though? These holes might be so small exactly because they popped up right after the Big Bang. The longer it took a black hole to appear, the larger it was. The mass difference between older, smaller, and younger, bigger black holes was incredible. Compare the mass 1,000 times greater than our Sun's and that of a jelly bean. Now you get it. There was a theory that primordial black holes could actually be dark matter. This matter is believed to make up around 80% of the mass of the observable universe. Astronomers can't see this bizarre ingredient directly since it doesn't emit light or any kind of energy. The idea remained unpopular for decades, but recently, scientists have realized there are many more black holes in the universe than they used to think, and it means the theory might actually work. And the vast and still hidden from us population of Big Bang black holes could not only make up but be dark matter. After all, astronomers haven't discovered a single dark matter particle yet, even after decades of searching. Some scientists argue that dark matter can't be tons of multi-sized primordial black holes. They would collide far too often for this to work out. Others object that black holes might exist in twos, and then a third one can always approach the pair and replace one of the initial holes. After all, our universe is swarming with black holes, and there's no lack of them. This process would repeat again and again, meaning there would be almost no merges or collisions. Primordial black holes might stay in clusters the size of the distance between our Sun and the nearest star. Each of these clusters can be home to thousands of black holes, all crammed together. A 30 solar mass monster of a black hole might sit at the center, with more common stellar ones occupying the rest of the space. Such clusters can be everywhere astronomers think dark matter is. But so far, this is still only an exciting theory, and some scientists don't support it yet. More data is needed. Now, black holes sometimes behave like massive galactic volcanoes. From time to time, they flare up, but instead of spewing lava, they produce enormous amounts of energy, and it makes gaping holes in the surrounding material and gas. A short while ago, scientists discovered one of the largest craters in the universe. Radio and X-ray telescopes detected a supermassive black hole that threw a temper tantrum many years ago. It happened in a galaxy cluster about 390 million light-years away from Earth. The crater left behind, which was actually a hole punched in the cluster's hot gas, could fit 15 Milky Way galaxies. Whoa. Recently, astronomers have found out that one of the most massive stars in the neighborhood might just have vanished. The star used to hover in space 75 million light-years away from Earth. It's usually too far away for scientists to clearly see individual stars, unless they're really massive, like the one we're talking about. It was gigantic and shining 2.5 million times brighter than our Sun. For the last time, astronomers saw the star's light in 2011, but when they decided to examine it more closely several years later, they couldn't find it. Such huge stars usually go out in an extremely bright supernova, but nothing here, which puzzled the scientists to no end. There's a theory it collapsed into a black hole, and it happened without triggering a supernova first. It does occur among stars nearing the end of their lives, but very rarely. KB 141b is a planet outside of our solar system. At first glance, it's not that different from Earth. It has liquid oceans that evaporate into clouds, condense, and get back to the surface as rain. But instead of water, this all happens with rock. The surface of the exoplanet is covered with lava seas tens of miles deep. The temperature on K2-141b reaches 5,000 degrees during the day. That's hot enough for the magma in the oceans to vaporize into the atmosphere. Then, supersonic winds, which can move at the speed of 1 mile per second, carry this rock vapor to the planet's night side. The vaporized magma cools down, becomes liquid again, and falls as a rocky rain. Well, looks like we're gonna need a bigger bumbershoot. A star in the galaxy GSN 069 might turn into a planet the size of Jupiter in the next trillion years or so, all thanks to the star's regular encounters with a black hole. First, astronomers noticed bizarre X-ray bursts. Those were super bright and went off every 9 hours. After examining this phenomenon, the researchers realized it was a star getting flung in a unique orbit around a black hole. and the flashes they saw were the material being slurped off the star's surface. It happened every time the star darted past its greedy host. Over millions of years, the black hole has already transformed the red giant into a white dwarf, and the process isn't going to stop anytime soon. Astronomers have recently discovered some traces of phosphine in Venus's atmosphere. On Earth, this colorless and flammable gas is often found near microbes. That's why a new theory claims there might be life on Venus. But if there is, it could only appear high in the clouds, because no living organism would be able to survive the planet's extreme environment. Its surface is incredibly dry, with no liquid water, and the pressure 90 times greater than that on Earth's surface. The temperatures there reach almost 900 degrees, hot enough to melt certain metals. So that's a no? Methane, a gas that's usually produced by living things, was found on Mars in 2013. European Space Agency's Mars Express spacecraft detected it in Gale Crater near the Martian equator. This discovery might one day answer the question if there's life on Mars. Asteroid 2019 OK scared scientists by sneaking up on our planet in July of 2019. This rather large rock, up to 400 feet across, appeared seemingly out of nowhere. It traveled uncomfortably close to the Earth, a mere 45,000 miles away. That's less than 1/5 of the distance to the Moon. The Sun's outer layer is way hotter than its surface. The temperatures vary from 10,000 degrees close to the surface and a mind-boggling 1 million degrees in the corona. That's the Sun's outermost layer. The reason for this phenomenon might be nanoflares. Those are regular, powerful bursts of heat from the star. Another theory blames the layer that lies just beneath the Sun's surface. It seems to generate a weak magnetic field. That's why, when the energy from this layer leaves the Sun, it heats the corona through a mesh of magnetic branches and roots. The Moon might still be shrinking. Our planet's natural satellite has become 150 feet skinnier than it used to be several hundred million years ago. If its insides keep cooling, it might explain the quakes shaking the Moon's surface. In 2019, NASA's InSight lander, whose goal was to study the interior of Mars, registered the first Mars quake ever. These quakes were coming fast, about 2 per day. Most of them were tiny. You wouldn't even feel them if they happened on our planet. So far, more than 300 Mars quakes have been detected. Those are the first quakes on any space body other than the Earth and the Moon. Another mysterious phenomenon discovered by the mission was bizarre magnetic pulses. They occurred every midnight around the lander. It's still unclear what those pulses are. Maybe after midnight they're gonna let it all hang out, or something. Pluto's atmosphere rises much higher above the surface of the dwarf planet than, let's say, Earth's. It also has more than 20 layers, all of them freezing cold and extremely condensed. Oh, by the way, our Moon also has some sort of atmosphere. Called an exosphere, it consists of helium, neon, and argon. It's 10 trillion times less dense than Earth's atmosphere. Or, really thin.
You may have time traveled multiple times already. You just don't remember it. A recent study says that all your memories of the trip would be completely erased as soon as you're back in the present. And you can blame it on something called entropy. To explain it, we first need to talk about closed time-like curves, or CTC. This is a closed path where a particle could travel, and it ends up right back at its starting point, at the exact same time it left. In other words, it's like a cosmic time loop. Take this notebook paper. Picture each line as a different timeline with a beginning, a middle, and an end. Now, if you roll that sheet of paper, the lines connect. Suddenly, they form a continuous line with no beginning or end. That's what CTCs are. Closed timelines that don't have a starting point. Past and present blend together in an eternal time loop. Now, a more practical example. You're taking a walk around a park. A woman jogs past you, and a dog starts barking. You keep walking, but then, wait a minute. You realize you're back at the exact spot where you started. The same woman jogs by, and the dog barks again. But here's the thing. It's not just that you've returned to the physical starting point of your walk. In a closed time-like curve, you're retracing not only your steps, but every single second of reality itself. Alright, now think about the big moments in your life. Being born, graduating from college, getting married. If all these events are part of one big time loop, that means time travel is possible. It sounds crazy, but there's a concept behind it called the self-consistency principle. It says that time travelers can't create time paradoxes. I mean, time travel can't just be this wild, chaotic mess like those crazy butterfly effect scenarios. Even if you go back in time, everything in your life still has to fit together in a way that makes sense and lines up with what we already know today. I'll explain. Let's say you go back in time and stop your mom from meeting your dad. But here's the problem. If they never meet, then you wouldn't exist. And if you don't exist, how could you have gotten into the time machine in the first place? That's a time paradox. That's why time travel could only work within these closed time-like curves. No matter what you do, the past, present, and future are locked in. They're always going to play out the same way, like a loop. Okay, so now you understand what CTCs are and why they're important for time travel to make sense. Now, we can finally talk about entropy and why it's probably the reason we'd lose our memory after a trip to the past. Entropy is a way to talk about disorder, chaos, or randomness in a system. Imagine a super clean, minimalist bedroom where everything is neatly arranged. Everything's in order. That's low entropy. But then, picture a messy teenager moving in. Every day, clothes, books, and random stuff gets scattered around the room. It's a mess. That's high entropy. In nature, things usually trend toward more disorder unless you actively work to keep them organized. Like this ice cube. It's made up of water molecules, all neatly lined up in perfect order. Low entropy. But if you take this ice cube out of the freezer, it will melt into water. See how the puddle looks messier now? In this form, the water molecules can be arranged in so many different ways. They're all disordered and random. And that's higher entropy. If we apply this idea to time travel within a CTC, the closed time loop, things get even more interesting. According to specialists, a key feature of this circular journey is that the level of entropy has to be the same at both the beginning and the end of the trip. Here's an example. You're just living your everyday life. Nothing too exciting going on, so the entropy level is low. But then, you get inside a time machine and go back to the past, right before you broke up with your high school sweetheart. By traveling through time, the chance of you changing the past and totally throwing your story into chaos is pretty high. Let's say you don't break up with her, and in this second chance, you decide to propose to her. See how everything could go totally sideways, right? So, when you go back to the past, the entropy is at a super high level. Now, you get to the exact moment when you're about to talk to your past love. At that point, entropy is at its peak. You're about to kneel down, show her the engagement ring, when, well, here comes the self-consistency principle, and it throws a cold bucket of water on this whole romantic idea. Remember, in a closed time-like curve, nothing can significantly change the present reality. All the changes a time traveler makes in the past can't cause any historical paradoxes. So, sorry to say, but you're not going to end up with her anyway. You decide to hop back into the time machine and return to the present. You get back into your routine, your job, and well, your single life. After completing the time loop, your timeline is back in order. Now, the level of entropy is low again, just like it was at the beginning of your journey. It's like you did a reset on the system. And that's the bad side effect of all this. Pressing this reset button would probably erase all your memories of the trip by the time you get back to the present time. Unlike in the movies, a time traveler probably won't recall anything. What? Now, answer in the comments. Even if you can't remember what you did after going back to the past, would you still take the risk? I'm guessing your answer would be, yeah, of course. That would be my answer too. After all, we could bring our phones and still make tons of cool photos on this trip, right? Well, no. This is where the laws of physics crush our hopes. Again. The second law of thermodynamics says that in an isolated system, entropy, or disorder, tends to increase over time. But this doesn't apply only to humans, but also to non-living things. It's why you can't unscramble an egg, unmix coffee from milk, or take your phone into a time machine. If a time traveler stores any data on their smartphone during their journey, experts believe it will probably get wiped out as soon as the trip ends. All the videos, photos, poof, gone. That's because machines probably wouldn't work properly when we go back in time. For example, let's say you bring a classic analog watch with you. For all the reasons we've already talked about, when you come back to the present, the clock needs to be exactly where it left off. I mean, the clock hands should be in exactly the same position at the beginning and the end of your journey. But to make that happen, it's likely that the frequency and number of ticks during the trip will be different. That could cause small problems in clocks made for regular time, making them unreliable. Something similar could happen with your phone. Its system probably wouldn't work as it should. All these consequences of time travel were described in a study by a mathematician published in 2024. While his theory doesn't determine whether time travel is actually possible, it does point out the strict conditions that would have to be met. And, well, it seems like having a time machine at home might not be as great as it sounds. In the end, you wouldn't remember a single thing about your amazing trip, and you'd probably just end up exactly where you are.
Now imagine something so powerful that it could rip the atoms of your body apart in a fraction. Astronomers have found a fast and powerful space object zooming through our home Milky Way galaxy at over 110,000 miles per hour, as faster than any rocket we've ever made. This bizarre space object got its name of a zombie star, all because it's the leftover part of a star that passed away a long time ago but is still moving. This zombie star is a kind of an object called a magnetar, a super small, super heavy ball about the size of a city but heavier than the Sun. That makes it one of the densest objects in space. Only black holes are denser. Hey, let's not forget about me, huh? Magnetars also have an incredibly strong magnetic field. The one our zombie guy has is 100 trillion times stronger than Earth's. That's so strong that if the magnetar came close to Earth, it could wipe out every credit card on the planet just from its magnetism, and we couldn't shop anymore. Plus, if a person got too close to a magnetar, like 600 miles or so, it could pull their very atoms apart, and they couldn't shop anymore. Luckily, this magnetar is very far away and not coming near us. When it was first discovered, it was about 15,000 light-years away from Earth. That's a huge distance, so you don't get to worry about your atoms being disconnected yet. Astronomers first spotted the zombie magnetar in 2008. And since only about 30 magnetars are known in our galaxy, it was a lucky and rare find. Scientists use space telescopes like Hubble and Gaia to watch it over time. That's how they discovered it was moving much faster than they thought. Now, astronomers are trying to figure out how this zombie star got such a big kick. At first, they thought that, like most magnetars, this one was born when a giant star exploded in a supernova and the leftover core became a super-dense neutron star. According to their theory, it could have happened near something called supernova remnant HB9. That would make sense since most magnetars are created this way. But when they tracked its movement, they found that the zombie star was moving too fast and going in the wrong direction to have come from HB9. They traced its path thousands of years into the past and still couldn't find any exploding star or star cluster it could have come from. This means scientists now have one more mystery on their hands. Where did this zombie star come from, and how was it made? One explanation is that it came from a white dwarf, which is the leftover core of a smaller star like our Sun after it runs out of fuel. Now normally, when white dwarfs explode, they're destroyed completely. But in rare situations, instead of blowing apart, a white dwarf might collapse into itself and turn into a neutron star. This neutron star could then become a magnetar. This unusual way of forming a magnetar also gives clues about another mystery: fast radio bursts, or FRBs. These are very quick and powerful flashes of radio energy from deep space. Some FRBs come from galaxies that are so old there shouldn't be any exploding stars left. But if magnetars can be born from collapsing white dwarfs, that might explain how those FRBs are still happening. In any case, learning how magnetars form could help us explain many strange and powerful events we see across the universe. But so far, the investigation is still on, and no answers have been found yet. Zombie stars wandering across the universe isn't the only mystery we haven't solved yet. At one point, you might come across one of them while traveling through the cosmos. It looks like nothing. At a distance of 700 million light-years away from Earth, there's a hole, a blank void that has very few galaxies. This is a roughly spherical region about 330 million light-years across. Our home Milky Way galaxy could fit there thousands of times over. It's the mysterious Boötes Void in the constellation of Boötes. Yeah, makes sense. You see, galaxies look like a giant web. Most of them are parts of long structures called filaments. Those wind through the cosmos, and when they meet, they form regions with a high concentration of galaxies. These regions are what we know as galaxy clusters. But between these clusters and threads, there are huge, empty voids that hardly contain any galaxies. Such voids make up almost 80% of the observable universe, and most of them are huge, from 30 to 300 million light-years wide. The Boötes Void is one of the most massive ones. It has even earned the title of supervoid. Astronomers think it might be the result of a few smaller voids merging. But what could have caused such giant empty areas to appear in the first place? The reason might lie in the origin of the universe. In its early days, I wasn't around then, all the matter in the universe was packed together quite tightly. Astronomers even thought it was something like a uniform soup. But soon, random quantum fluctuations started disturbing this matter. Some areas became denser, and their gravitational pull became stronger. They began stealing matter from less dense regions. This made such areas even denser, and they kept attracting more and more matter. At the same time, smaller clumps of matter started drifting further away from the center, forming galaxies. If you visited a star cluster called Palomar 5, you'd forget all about voids and supervoids and even zombie stars. Instead, you'd need to concentrate on surviving, since the region is hiding a swarm of over 100 black holes right in the middle. And those black holes aren't just sitting there, they're at work, shaping the cluster nonstop. Palomar 5 is a group of stars located about 80,000 light-years away from us. Normally, clusters like this are dense and tightly packed, with stars all bunched up together. But Palomar 5 is different. It's spread out and has a huge tail of stars, stretching across 30,000 light-years. This beautiful tail is called a tidal stream. It's like the stars are spilling out of the cluster, creating a long river of light. Tidal streams like this are rare and hard to study. Globular clusters like this one are super old. Some are almost as old as the universe itself. But Palomar 5 also stands out because it's the only cluster we know about that still has a tidal stream attached to it. And the black holes inside the cluster might be to blame. They're pulling on the stars in the cluster, messing with their orbits, and slingshotting them right out of the cluster. Or would that be slingshooting? I don't know. Anyway, these stars are what make up the tidal stream. Over time, more and more stars get flung out. Palomar 5 has way more black holes than expected. About 20% of the cluster's mass is made up of black holes, over 100 of them, each about 20 times the mass of our Sun. Of course, Palomar 5 isn't going to last forever. In about 1 billion years, the cluster will completely fall apart. By then, all the stars will have been gone, leaving behind just the black holes. And these black holes will orbit the Milky Way, like a ghostly remnant of a cluster that used to be there. Even though this cluster is creepy enough, there's something even more eerie you can see in space: thick clouds of gas and dust called nebulae. One of the most unusual ones is probably NGC 2392, located 5,000 light-years away from Earth in the constellation of Gemini. It was discovered more than 200 years ago and became popular because of its unusual appearance. It's basically a disk of material with a ring of comet-shaped objects. The tails of these objects stream away from the star at the center of the nebula. The bizarre orange streaks in the outer part of the cloud stretch light-years away in all directions. The middle resembles a ball of twine, but in reality, it's a bubble of material blown into space by the wind of high-speed material.